On October 16, 2025, an extraordinary and truly sensational breakthrough in astronomical observations occurred, prompting scientists around the world to reconsider the mysteries of the cosmos and challenging many established notions. This time, it concerns a recently emerged image obtained with powerful telescopes and processed based on data collected in the first days of August of the same year. This image, like a lightning bolt, struck the scientific community, causing a wave of bewilderment, surprise, and new questions. The photograph clearly captures an object, something that ejects a long, approximately 6,000 kilometer long tail directed straight toward the Sun, rather than away from it, as is typical for most celestial bodies known to us. This unusual feature became the basis for serious reflections and debates among experts. The phenomenon is so strange and unnatural that immediate questions arise. What is this object? Could it be a comet, or perhaps some new form of cosmic body that we had no prior knowledge of? Today, we will attempt to analyze all the clues and details of this mysterious image step by step to understand what is truly happening in this cosmic spectacle. By the end of our investigation, we will uncover something so astonishing and radically changing our understanding of comets and other celestial objects that many existing theories will need to be reconsidered. Moreover, the facts we have discovered could lead to a real revelation, an unexpected breakthrough in our understanding of space, a scientific revolution. If, like me, you are interested in these secrets and mysteries that surround us, do not remain indifferent or simply watch from the sidelines. Get involved in the process, become part of this incredible search for the truth. It is important to remember that your support and participation help us continue to uncover the secrets that have so far remained out of reach for most. In this context, it is crucial not to forget the importance of carefully following developments, analyzing each new piece of information, sharing your thoughts and impressions. Each of us can contribute to this great effort by sharing this video or information on social media platforms like X, Facebook, Reddit, or simply in personal chats. Because it is precisely through your activity and interest that we can continue studying and unraveling the mysteries that seem hidden beyond the boundaries of our usual knowledge and perceptions. This channel exists thanks to you, and your support is the main motivation for us to keep searching and analyzing those mysteries that most will never even touch. Now, let's move on to the first part of this astonishing story, about an image that, in essence, should not have existed. On October 16, 2025, the astronomical world was shaken by an event that seemed impossible. On that day, images based on data collected in the first days of August of the same year appeared on Telegram channels and scientific forums. These data were obtained using the 2-meter Tidy telescope located in the Canary Islands. The most astonishing aspect was that the image that circulated turned out to be so contradictory to all existing laws of physics, so scientifically incorrect, that all astronomers on the planet halted their research and essentially froze in place, overwhelmed by amazement and bewilderment. Imagine this scene. At the center, there is a black, nearly circular mask that seems to cover the bright light of an object, making it barely distinguishable. Surrounding this mask is a bright halo, the expected dust coma characteristic of most known comets. However, from this cloud of gas, dust, and particles suddenly erupts something else, a narrow jet, faint but unmistakably identifiable. This jet, approximately 6,000 kilometers long, seems to cut through space, heading straight toward the Sun. And it is precisely at this moment that, imagine a grand display of nature, a water jet ejected from a fountain suddenly begins to move back into the nozzle, as if the flow of air or liquid itself decided to reverse, defying all usual laws of gravity and physics. Or imagine smoke rising upward into flames, but suddenly, instead of ascending, it begins to descend, as if being pulled back into the source of ignition. Such metaphors help convey the degree of anomaly and surprise we face when observing certain astronomical phenomena. It is quite possible that at the center of this is an antipolar direction, an area where, according to our assumptions, brightness, movement, and activity should prevail, but instead, complete darkness or dim glow is observed. This empty, or dim, region seems indifferent, ignored by our expectations, like an invisible zone where nothing happens. Meanwhile, along this trail, directed toward the sun, stretches a long, curved line, like an accusing finger pointing at our star. This line seems to tell us something important that we do not yet fully understand. Scientists studying these mysterious phenomena work with models, creating complex structures and hypotheses to explain what they have seen. These models serve as a kind of map, helping to predict what should happen in similar situations based on known physical laws. They allow for hypotheses about the future behavior of comets and other celestial bodies, as well as explanations for what has already been observed. However, sometimes when nature reveals something unexpected to us, these models begin to collapse like a house of cards, confirming that there are gaps in our understanding. Such a shock is happening now, as an image has appeared that not only challenges existing comet models but actually destroys them, completely overturning our previous notions. If it is confirmed that the observed feature is not a random artifact or a result of complex image processing, but truly an objective fact, then we will have to reconsider all our ideas about the nature of these ancient cosmic travelers. This discovery has the potential to change the entire picture we have built about comet behavior, their composition, movements, and properties. The consequences of such a discovery spread like cracks across ice. They diverge in all directions, triggering a chain reaction of re-evaluation and new questions. We must ask ourselves, could this be evidence of a completely new class of objects previously unknown to astronomy? Or perhaps it involves some exotic physical process, unique to such bodies and never before observed within our solar system? Maybe it is not just another mystery but a hint at something much stranger and more astonishing that forces us to reconsider even the very term comet. Why does this word no longer seem suitable to describe what we are currently seeing? Could it be that the observed objects or phenomena possess properties that do not fit into the familiar categories we are used to working with? There are no definitive or final answers to these questions yet, and it is precisely this extraordinary state of uncertainty that makes the current moment so exciting and significant for science. Before delving into the interpretation and meaning of these discoveries, it is essential to acknowledge one important fact: astronomical images, especially those obtained with modern sensitive instruments and complex signal processing methods, are not always completely reliable. They can create illusions, show ghosts, artifacts, or patterns that do not actually exist in reality, but are merely the result of data processing peculiarities or random noise. The technology of non-lamp filtering, widely used to enhance faint structures and details in images, although highly effective, is not without drawbacks. It can amplify not only the desired signal but also noise, creating false contours and shapes. Part 4 of 58. During long exposures, when the camera captures an image over an extended period, false images often appear due to movement. When astronomers begin publishing articles that pay special attention to a jet directed toward the sun, considering it no longer just an unusual or accidental phenomenon but a fully real object requiring scientific explanations and confirmations, we understand that the line between skepticism and acceptance of this phenomenon as part of reality has long been crossed. This is an important milestone, marking the beginning of a new stage of perception, from initial disbelief and disregard to awareness and possibly even admiration. The upcoming events and research will determine whether this object can alter our conventional understanding of small celestial bodies, their nature and origin, or if it will open doors we had not previously even suspected, expanding the boundaries of our knowledge. Time inexorably moves forward, and in the coming days, 2 automated spacecraft launched specifically to study this region will pass through the nearest segment of space to Earth, and their instruments may record data that could either confirm or refute our current hypotheses and interpretations. But before we reach this critical moment, we need to understand how deep and mysterious this rabbit hole into which we have fallen truly is. Because the sun will continue to shine, and this is only the beginning, ahead lie discoveries that could change our view of the universe. The chemical composition and properties of matter emanating from this unusual object tell a story so impressive and complex that even an airplane seems, in comparison, an almost ordinary and simple object. The second part of this story is the confirmation of the presence of a solar tail, which, apparently, originates precisely from this mysterious object. Before allowing ourselves to believe in what seems impossible, it is important to eliminate all possible conventional explanations and assumptions, for this is the greatest gift of the scientific method: the ability to critically and meticulously analyze facts. At the same time, this is its most disappointing trait, because every new unusual discovery demands from scientists not only openness but also constant skepticism. When you encounter something unusual or mysterious, your first task is not to rejoice prematurely or draw hasty conclusions, but rather to begin with reasonable and cautious doubt. This complex and delicate game involves not only astronomy but also image processing art and even elements of forensic science. At the core of it all is the very process, from collecting photon signals traveling through interstellar space to their arrival at a detector, where they are transformed into electronic signals. These signals are then subjected to mathematical transformations, allowing the detection of structures and objects that are too faint and subtle for direct observation with the naked eye. Each stage of this complex process carries a risk of error. Background noise, which can obscure real objects, may mask them, creating the illusion of their presence. Cosmic rays, when hitting the detector, leave bright streaks and traces resembling jets of matter ejected from celestial objects. Stars captured in long exposures appear as lines that can randomly align with interesting directions or structures, complicating data interpretation. Deconvolution algorithms used to enhance the sharpness of blurred images can distort real features, turning them into false artifacts, which makes correct interpretation more difficult. Experts working with 3 different telescopes are well aware of all this, a team that has been analyzing such images for decades. They didn't simply run images through filters and stop there. They carefully examined the background star contamination, studied numerous observation series to determine whether the detected feature persists or disappears, and whether it is consistent with a real physical trail or merely a processing artifact. These scientists compared results obtained from different instruments. By the end of July and early August, previously conducted observations already hinted at the existence of unusual phenomena that seemingly should not occur within the framework of typical cometary activity. These early discoveries revealed mysterious trails appearing at angles inconsistent with standard models or expectations of comet activity. For those unfamiliar with the terminology, it is worth explaining that the position angle is a way of measuring direction in the sky, where 0 degrees indicates north, 90 degrees east, and so on clockwise. Usually, when considering a comet's tail or related phenomena, it is assumed that its direction is anti-solar, determined by the geometry of the comet's orbit and the current position of the Sun relative to the observer. Within the framework of the model for Atlas number 3 with the letter I, this implies certain standardized angles. However, during observations of this unusual phenomenon, it became clear that the direction indicated by this mysterious trail did not match the expected anti-solar direction. Moreover, it was located in a region where, according to calculations and theoretical models, such structures should not appear. As a result, several independent research groups began systematically rechecking their initial data to exclude the possibility of errors or artifacts. Part 6 of 58. The images taken by the Hubble Space Telescope, which has exceptional resolution and allows us to see the tiniest details in the comet's structure, have gained particular importance. These images revealed asymmetry in the shape of the coma, indicating the presence of potential anomalies or special processes in its environment, all against the backdrop of Earth's turbulent atmosphere, which complicated data interpretation. At the same time, ground-based observatories located in places like Spain, Chile, and Hawaii independently recorded unusual features in the observed phenomenon. All of this was not happening in a vacuum. Astronomers constantly communicate, share results, compare their observations and conclusions. When several independent teams begin to record similar anomalies, it becomes clear that the issue is not due to random errors or artifacts, but to real phenomena. Explaining such consistency becomes increasingly difficult, and attempts to dismiss everything as technical glitches or artificial illusions seem unconvincing. In fact, one can imagine that we are witnessing some unusual event that leaves traces in data collected from different locations and with various instruments. If someone tells you they saw something strange, you would undoubtedly be skeptical, as human perception is prone to errors, and illusions and artifacts can easily be misleading. However, imagine a situation where 10 people scattered across the city describe the same mysterious entity observed from different vantage points, using different cameras and devices, at slightly different times, yet all characterize it with the same details. In this case, your attitude towards their words should change. Such a situation has occurred with the phenomenon known as sunwood jet. Too many eyes, too many instruments are involved, and importantly, the sequence of observations speaks for itself. The technical details related to data processing play a crucial role because they allow us to distinguish bold hypotheses and guesses from objective observations. When scientists apply non-lamp filtering techniques, they are essentially searching for boundaries and regions of brightness heterogeneity, enhancing image contrast to reveal the tiniest details. This method has been studied and refined for a long time. We know what artifacts it can produce and how to distinguish real objects from artificial ghosts created by processing. In the case of sunwood jet, observations show characteristics consistent with a three-dimensional structure emanating from the core of the object, rather than a flat, two-dimensional one. Increasingly, scientific articles suggest the existence of a directed jet ejection aimed at the sun. The main focus of these studies is on its possible nature and explanation, rather than denying its existence. Part 7 of 58. This approach represents a significant shift in perception. Whereas scientists previously tended to consider such a phenomenon as merely a hypothesis or a potential coincidence, now it is about acknowledging its likelihood, moving from the question, "Is this real?" to a more calm, "Is this probably so?" This transition not only changes the tone of the discussion but also alters the very paradigm of how the observed phenomenon is perceived. Importantly, the second question, about the nature and composition of this jet, turns out to be much more intriguing and simultaneously alarming. Because if such an outburst truly exists and constitutes a flow of matter rushing toward the sun's surface contrary to all our previous understanding of comet physics, then it becomes necessary to understand what exactly is emerging from this outflow into the surrounding space. It is essential to thoroughly study its chemistry, determine its composition, and find the fingerprints of the substances creating this unusual fountain. When scientists conduct spectroscopic studies, directing their instruments at these mysterious regions, they discover something so astonishing and strange that it can almost be said to be as extraordinary as the very fact of the jet's existence. The spectra reveal the presence of nickel where, according to standard models, iron should be. Carbon dioxide is detected where, logically, water should be present, and the element ratios observed do not match the usual patterns for typical comets known in our solar system. This jet itself is a visually striking anomaly capable of stunning the imagination of any observer. But it is precisely the chemical composition and its anomalies that truly make one think and evoke concern. The so-called third part stands out especially sharply: nickel without iron. If we assume that this jet indeed exists and its existence is increasingly confirmed, a clear and important question arises. What exactly is emerging from this unusual outflow? In the course of comet studies, scientists are essentially conducting a kind of forensic analysis of the chemical composition from a distance. The influence of sunlight on molecules in the coma excites them, after which they relax, emitting photons, particles of light, at specific wavelengths. Each chemical element or compound has its own unique spectrum, a so-called fingerprint, which very precisely reflects its presence and relative abundance compared to other substances. By studying the spectra, breaking them down into component colors, and measuring the intensity of emissions at various wavelengths, specialists can determine which chemical elements are present in the cometary cloud and in what proportions. For this, they use some of the most modern and powerful spectrographs available today. For example, the 31st ATLAS telescope, located in Chile and equipped with an ultraviolet spectrograph, obtained high-resolution spectral data at various times as the comet approached the Sun. The results of these observations were, to say the least, quite unexpected. The spectra revealed a bright and very strong emission line of neutral nickel atoms, which dominated certain wavelength ranges. This was not just a subtle hint or a weak signal, It was a clear, expressive, and unambiguous indication that said, nickel is here. In fact, the detection of metals in comets is not at all a new or unusual phenomenon. Many comets contain dust particles that include refractory elements such as iron, magnesium, sodium, nickel, calcium, and others. When these particles undergo sublimation, transforming from solid to gas, or are exposed to intense solar radiation, these metals can enter the gaseous phase and emit their characteristic spectra. However, it is typical for the universe to encounter various metals much more frequently than nickel. These metals are especially common in meteorite material, making their presence a routine aspect of astronomical research. In most cases when studying celestial objects, we expect to see iron predominate over nickel, since it is far more abundant and widespread. Yet, surprisingly, in 3 different atlases, observers recorded an unusual phenomenon. During certain periods, nickel emission reached significant levels, while iron emission virtually disappeared. Such a phenomenon was so astonishing that scientists use a special term, extreme abundance ratio, to describe these situations. And it indeed seems very strange, as such observations contradict everything we are accustomed to consider normal. In some cases, the ratio of nickel to iron was so high that the difference exceeded all previously recorded values in other comets. One can imagine a scenario where some unusual, almost fantastical comet, subjected to special conditions, somehow filtered out most of the iron, leaving only nickel in its composition. Nature, as a rule, does not act with such selectivity, and therefore these observations are of genuine interest and require explanation. But the situation is not limited to chemical mysteries. It becomes even more complicated when we turn to astronomical instrumentation. The James Webb Space Telescope, recognized as one of the greatest achievements of modern infrared astronomy, is currently fundamentally changing our understanding of the universe. It has directed its highly precise instruments at 3 separate atlases, and the results have been astonishing. The JWST telescope specializes in observing in the infrared spectrum, making it particularly suitable for detecting molecules such as water, carbon monoxide, and carbon dioxide, which play a crucial role in the chemistry of cosmic objects. And here is what was discovered: in the composition of the coma, that is, the original gas cloud surrounding the comet's nucleus, it was not water as one might expect, but carbon dioxide. The ratio between these 2 substances was approximately 8:1. It is worth repeating these figures: 8 times more carbon dioxide than water. It should be emphasized that most known comets within the solar system can be described as dirty snowballs, where water ice is the primary volatile component. In addition to water, such bodies contain other gases: carbon monoxide, carbon dioxide, methane, ammonia, and other frozen substances. But water always dominates in quantity. It is precisely the lightest and most easily sublimating substance when a comet approaches the Sun and becomes active. Rare cases of comets with high carbon dioxide content are astonishing exceptions, and even among them, the ratio of 8:1 stands out as a particular extreme. What could explain such strange chemistry observed in these objects? Scientists immediately began searching for possible natural mechanisms that could lead to such results. One of the most interesting hypotheses is the idea of metal-carbon compounds. In space, there are molecules where metal atoms are bonded with groups of carbon monoxide. For example, nickel tetracarbonyl with the formula Ni, CO4 is a real chemical compound formed under certain conditions. Its iron analog is pentacarbonyl iron, denoted as Fe, CO5. Both of these substances are volatile, meaning they can sublimate at relatively low temperatures, significantly lower than those at which pure metals typically sublimate. If these compounds were present in some of these bodies, their decomposition could release nickel and iron atoms along with carbon monoxide. However, the problem is that forming such compounds requires very specific conditions. Maintaining their stability in space is challenging. Let's delve deeper into how various chemical compounds decompose under the influence of ultraviolet radiation, which is abundant in space. In this airless and cold environment, ultraviolet rays from the sun penetrate freely and actively participate in breaking down molecules. For compounds like 3IATLAS to form and persist in space, a special environment is needed. One that is extremely cold, reductive, and stable enough to slow down decomposition processes. It is quite possible that unique conditions for the formation of such substances existed in some exotic environments, for example, around bright carbon stars surrounded by dense clouds of gas and dust, or within molecular clouds with extraordinarily rich chemistry, where temperature and radiation levels created favorable conditions for the synthesis of complex compounds. These hypotheses undoubtedly require serious scientific confirmation. However, they are not without merit, considering that there are indeed regions in space with unusual conditions different from those we are accustomed to. Nevertheless, even if we assume that such compounds could form in rare and mysterious areas, this still does not provide a complete explanation for the observed ratio of nickel to iron. In particular, the question remains as to why nickel dominates in the celestial objects under study, while iron is present in smaller amounts. Even when considering metallic carbon compounds, alloys containing nickel or iron, the question arises: why do nickel carbon compounds sublimate at lower temperatures compared to iron? The sublimation temperature thresholds of these metals differ, but not enough to fully account for such a discrepancy. This suggests that within the comet's core, there must be a special thermal environment capable of displacing nickel without affecting iron. When the comet approaches the Sun and the surface and interior temperatures rise, a natural question emerges: will iron be released from the inner layers? Some observations confirm that this indeed occurs. For example, scientists have noted that iron emission becomes noticeable only when the comet's trajectory crosses a distance of about 2.6 astronomical units from the star. This fact aligns with a temperature-dependent release mechanism. However, such a process requires a very specific internal structure or composition gradient within the comet's core, allowing certain elements to separate from others as the temperature increases. This creates a complex model, suggesting the presence of distinct layers or regions with different chemical compositions. Some scientists, discussing these hypotheses perhaps in a relaxed setting, over a cup of coffee or during a break at the observatory, may have begun to propose more exotic and even fantastical ideas. What if part of this celestial object is not natural at all? What if its composition includes materials processed or specially designed by humans, based on technologies utilizing nickel alloys widely used in our industry? Examples include stainless steel, which contains a significant amount of nickel, or superalloys used in turbines and engines, as well as anti-corrosion coatings and other materials. Nickel in these alloys provides high strength and resistance to wear and corrosion, making them indispensable in harsh operating conditions. Additionally, nickel cyanide is used in plating and electrochemical processes. If we imagine that alloys with a high nickel content are used for constructing interstellar ships or probes precisely for these reasons, reliability, durability, and stability, then a question arises: how justified is the assumption that such materials ended up in space exactly in this form? We must exercise extreme caution because the transition from unusual cosmic chemistry to assumptions is delicate. When it comes to patterns in the behavior of cosmic objects, there is often a desire to find simple explanations for complex phenomena. However, sometimes observations reveal aspects that are difficult to attribute to obvious causes and require deeper analysis. One such mysterious case involves the behavior of a particular object known as the Triple Atlas, or more briefly, the 3 Atlases. This celestial body exhibits not just chaotic gas emissions but something far more complex and astonishing. It pulsates with a certain periodicity that is visible to the naked eye. Note that this object does not simply release gas gradually and evenly into space, as is typical during ice sublimation when ice evaporates under solar heat and gradually turns into vapor. Instead, what we observe is different. It pulses like a living heart, beating with precise regularity, similar to a rhythmic tempo. The period of this pulsation is approximately 4 hours, which stands out as a key characteristic. During this time, the brightness of the object and the intensity of the emitted gas change with a regularity clearly observable in the data. Even more interestingly, some evidence suggests the existence of a second, shorter period, about 2 hours, which appears to be linked to the main cycle in harmonic relation. Imagine a heartbeat, a steady and rhythmic pulse indicating that inside this cosmic body there is a mechanism that switches activity on and off with mechanical precision. This rhythm resembles the workings of complex clocks, where everything moves according to a strict schedule. Such regular cycles in nature typically result from an object rotating around its axis. The simplest and most logical explanation for why a comet or similar object exhibits exactly a 4-hour activity cycle is the assumption that its core rotates with a period of exactly 4 hours. During this rotation, active regions on the surface come into and go out of sunlight, disappear, and reappear. Consequently, the activity associated with gas emission and luminescence changes systematically in sync with the core's rotation. This explanation is neither new nor unusual. On the contrary, many comets in our solar system have elongated, irregularly shaped bodies made of ice and rock that drift through space. If, in certain regions, the nucleus contains sources of gas jets, such as exposed deposits of volatile substances or a surface structure that directs gas flows in specific directions, then, during rotation, these jets will appear and disappear depending on the viewing angle and sunlight illumination. This is a logical and natural explanation commonly encountered in astronomical observations. For example, some comets exhibit periodic outbursts of activity related to their rotation, which supports this hypothesis. If we assume that all observed phenomena are due to rotation, then a 4-hour activity cycle seems quite reasonable and does not contradict existing theories. If this is the case, then the observed pulsation provides valuable information that broadens our understanding of the nucleus's shape and the distribution of activity on its surface. It helps us comprehend how energy escapes from within, how the internal structure of this object is arranged, and how it interacts with sunlight. However, such a mechanism does not undermine the fundamental principles of physics nor cast doubt on the existing laws of nature. Let us delve a little deeper into what requires such an explanation. For rotation to produce a stable, regular signal of brightness and gas emission, very strict conditions must be met. First of all, there must be an active region or a group of such regions with high stability over time. Next, the nucleus's shape must be precisely defined, with minor surface irregularities that could interfere with synchronized movement. Factors such as uneven heating, caused, for example, by the orientation and placement of active zones, or changes in the distribution of underground ice are also important, especially as volatile reserves are depleted. The physical aspects related to comet studies often seem quite clear and understandable to specialists. In particular, considering the comet as a system composed of two connected or separated nuclei could explain the observed periodicity in its behavior without resorting to overly complex or unusual hypotheses. Such a scenario suggests that two interconnected components within the nucleus may rotate with a certain degree of synchronization or follow a characteristic mutual orbit, which could manifest as regular variations in brightness or activity. However, convincing confirmation of this hypothesis requires sufficiently precise and detailed images of the nucleus, and unfortunately, we do not yet have such images. The object is too distant and too faint for our most powerful telescopes to directly observe its internal structure or nucleus in detail. As a result, we are forced to operate with indirect data, drawing conclusions based on the analysis of its light curve and behavior, which naturally leaves room for doubts and assumptions. Moreover, an equally important aspect is the potential bias of the observations themselves. The periodicities we detect may be the result of our data collection methods rather than actual characteristics of the object. For example, since many telescopes and observational programs operate on a fixed schedule dictated by technical limitations, schedules, and Earth's rotation, they can inadvertently create the illusion of regular cycles. Regular observation intervals often lead to noisy signals being interpreted as periodic phenomena, even though they are not truly periodic. Astronomers are well aware of this and employ various statistical methods and algorithms to minimize such artifacts, but it is often impossible to completely eliminate their influence. Therefore, the question arises, could the actual 4-hour period observed in the data correspond to reality, or is it merely the result of random fluctuations and distorted signals? By studying numerous independent observational campaigns conducted by different groups of specialists under various conditions and with different instruments, it becomes evident that the results over time show some consistency. This suggests that the 4-hour period is most likely not just a coincidence or a technological artifact, but indeed reflects some physical phenomenon. However, despite this, it remains necessary to exercise extreme caution and a critical approach to interpretations, as science always carries the risk of misperceiving the data. Now, let us move on to a more speculative part of the discussion. What if the hypothesis of purely standard physical mechanisms does not explain the observed periodicity? If the 4-hour period is not a coincidence but a real effect that cannot be attributed to rotation or simple core movement, what else could be causing it? Is there a possibility that within the core there exists some special system or mechanism that periodically releases volatile substances? Imagine that inside a comet there is a reservoir or a set of chambers where gas or other volatile components accumulate, and then, upon reaching a certain pressure or level of saturation, they are suddenly released through specially designed holes or vents. Such mechanisms could explain regular outbursts of substances and the associated changes in brightness or activity. In a natural comet, the pressure inside its core increases as ice sublimates beneath the surface, eventually causing a rupture through weak spots. Typically, these emissions are chaotic and irregular, caused by faults, cracks, or collapses that do not follow any consistent pattern. They resemble flashes that occur randomly and with varying intensity rather than well-organized cycles. Therefore, a regular 4-hour cycle seems unusual and raises questions. Either this is an extraordinary coincidence of natural conditions, or there is something more organized at play. If we imagine that within the core there are chambers or pockets where gas and volatile substances accumulate and then release, this idea might seem so fantastical that it's hard to believe in its reality, since what we're talking about is quite science fiction. However, in essence, this is how it is perceived, at least until we have even a single piece of evidence confirming its existence or making it more convincing. Still, when we consider the phenomenon associated with the 4-hour impulse, combined with the Sunwood jet aircraft and the chemical compounds prevalent in nickel alloys, one additional mystery emerges, adding another layer of strangeness to the already numerous odd facts. Moreover, there is another aspect worth examining separately. Imagine that in the process of gas emission, compounds containing carbon and metals are involved. If the formation or breakdown of these compounds occurs through a cyclic chemical mechanism, it could lead to periodicity in the observed phenomenon. In that case, one could envision a feedback loop. Heating causes sublimation, and the sublimation process itself cools the surface of the object. Subsequently, cooling promotes the recondensation of carbon, and the cycle repeats. Such a mechanism is thermodynamically plausible, provided that suitable conditions are present in the surrounding environment. However, to trigger such a reaction, a very specific chemical environment is required, along with extremely stable conditions inside the core or its vicinity. This explanation is not the first that comes to mind, and it may seem quite fantastical, but it cannot be entirely dismissed, as it remains a plausible possibility. It is important to note that the 4-hour impulse is yet another significant detail that raises questions, since it does not fit into conventional models and theories. When considered separately, it is intriguing and can be explained if certain features are taken into account. But together with all other observations and facts, this detail only enhances the impression that the 3IATLAS objects are entities that seem to follow their own special rules. And now the question arises: are these rules applicable only to these specific objects, or do they point to the existence of a broader category of interstellar bodies or ships, which we are only beginning to learn about and understand? Because this is the true, urgent reality, we do not intend to remain inactive and delay the study of this object for many years. We have only one chance, a narrow window, during which we can obtain the most detailed data using spacecraft that happen to be in the right place at the right time. It is precisely now that this window of opportunity opens, and it will not come around again very soon. Over the next few days, instruments aboard 2 different space missions will begin exploring the surrounding cosmos, deliberately pointing their sensors at the discovered mystery. The results of these observations, What they find or do not find could shape our interpretations and understanding of this phenomenon for many years to come. In this case, we are talking about a crucial, literally life-changing test that could alter our perception of interstellar objects and how they interact with their environment. Our available time is very limited, and this is essentially our only chance to see this mysterious object up close, in person, under real conditions. After all, encounters between artificial spacecraft and unusual celestial bodies are extremely rare in the vastness of space. Such moments are truly precious opportunities, occurring once every decade or even less frequently. They are created either through long-term planning or, more fortunate still, by chance circumstances. The 3IATLAS objects suddenly appeared in our solar system, as if out of nowhere. They followed orbits we did not anticipate or expect, becoming noticeable only after they circled the Sun and began their journey toward the outer boundaries of the solar system. Unfortunately, we cannot send a mission to them at this moment. When the Hera spacecraft approaches asteroid 3IATLAS, it will be approximately 8 million kilometers away. Although this is not a close distance by space standards, it is still sufficiently small to allow onboard instruments to record and gather important scientific data. This interval is not a full flyby or rapid pass, as in a very close encounter, but it is close enough to ensure high-quality observations and measurements. At this moment, the instruments will be able to obtain valuable information about the asteroid's surface and the surrounding dust environment present within it. The Hera spacecraft is equipped with cameras, spectrometers, and particle detectors designed to study the surface structure and composition of dust particles, as well as the features of the surrounding environment. These instruments can, at least partially, be redirected to observe the comet's coma and tail, greatly expanding the scope of the research possibilities. Such an opportunity is not unique. Similar tasks are assigned to NASA's Europa Clipper spacecraft, which is scheduled to travel to Jupiter's moon, covered with a thick ice shell, between October 30th and November 6th. In this case, despite the millions of kilometers of distance, the use of such technologies allows us to obtain valuable information about objects located in the distant corners of our solar system. Of course, Europa Clipper will not be able to see the moon's core in detail or take large-scale surface images that reveal the tiniest features. However, its spectrometers will be able to analyze the light passing through the comet, providing the opportunity to determine its atmospheric composition and structure. Additionally, the spacecraft's instruments can detect and record charged particles that are released from the comet under the influence of the solar wind. Their plasma detectors can identify and analyze these plasma flows, while magnetometers can record the presence and variations of magnetic fields in the region where the interplanetary magnetic field interacts with the ionized gas cloud formed around the comet. All these measurements, combined, give particular value to such missions, as they allow for a broad spectrum of complementary data. Optical observations from Earth provide a macro view of the comet's structure. Main shapes, jets, and flow phenomena can be seen. However, these methods cannot distinguish the chemical composition of individual particles or determine their physical properties in detail. Spectroscopy performed with ground-based telescopes can establish the comet's chemical makeup, but limitations related to Earth's atmosphere and the object's brightness often hinder obtaining the most accurate and detailed data. Meanwhile, instruments on spacecraft, even from a considerable distance, have the ability to work with wavelength ranges inaccessible to ground observations, since the atmosphere blocks their passage. This allows for direct measurement of particle properties, identification of their composition, and observation without distortion caused by atmospheric effects. If missions like Hera or Europa Clipper detect strong radiation associated with the presence of nickel in the coma, it will serve as an independent confirmation of the spectroscopic data obtained from Earth and indicate unusual chemical activity. Maps of the coma's structure, if created using data from spacecraft and revealing asymmetries corresponding to solar wind streams, will convincingly confirm the presence of physical features rather than accidental artifacts or measurement errors. Additionally, if plasma detectors record unusual ion content or detect unexpected particle types, this could indicate the presence of exotic chemistry in the coma or the release of substances from the nucleus that are not found in natural conditions. Conversely, if the data from the spacecraft indicate that the comet is in a normal state, with its chemical and physical composition within standard parameters and no anomalies detected, this will force scientists to reconsider previous assumptions. When such situations occur, space instruments specifically designed to study and measure the parameters of the local space environment near our planet will suddenly find themselves in a plasma-filled environment related to comets. Equipped with modern sensors and detectors, these devices will be able to detect ions of various molecules that enter their detection zone as a result of ionization of substances constituting the comet. Onboard laboratories will record water ions, carbon monoxide ions, as well as carbon dioxide ions. Metal ions, such as nickel and iron, are also not excluded if their presence is significant in the comet's tail. Mass spectrometers installed in these complex systems can distinguish different types of ions based on their mass-to-charge ratio. This provides a unique opportunity to obtain direct data on the composition of the comet's tail, not limited to conclusions drawn solely from spectroscopic information, thereby greatly expanding our understanding. Through these measurements, we can determine exactly what is in the tail, rather than relying solely on indirect indicators. Additionally, magnetometry is another important tool that allows us to diagnose the interaction between the solar wind and the comet. When the solar wind encounters a comet, it forms a so-called magnetic envelope around it, creating a characteristic pattern that reflects the physical processes occurring in this region. The shape and strength of this magnetic shell depend on numerous factors, including the gas emission rate from the comet, its composition, and the efficiency of ionization processes and ion interactions with the magnetic field. If the results deviate from expected models, this may indicate the presence of unusual physical phenomena in the plasma or atypical conductive properties of this region. Such deviations could point to complex chemistry or unique properties of the materials making up the comet's tail. However, it is important to keep realistic expectations in mind. These spacecraft conducting research do not perform specially planned flybys in close proximity to comets. Their schedules are very busy, and the main mission objectives do not include participating in numerous flybys like those conducted, for example, by the Astrodesk spacecraft or other research platforms. For instance, the HRA spacecraft, which needs to establish contact with the Defies space object, must focus on fulfilling its primary tasks. Europa Clipper, in turn, must maintain its power and momentum to successfully reach Jupiter, and fuel is required to make trajectory corrections when targeting the comet. All of this competes with other priority observations and may result in scheduled activities being missed. The distances at which measurements are taken limit the resolving power of the data obtained, so we cannot expect to create detailed surface maps of the comets or identify large active sources of material emission. Instead, we receive contextual data that provide insights into the surrounding environment's composition and some properties of the comet. Nevertheless, there are time-related challenges. Flybys occur over a few days, during which the comet moves, changes, and possibly becomes more or less active, reacting to external cosmic influences or internal processes. As a result, proper coordination of observations, precise instrument targeting, and data collection at the most critical moments require careful planning and even a bit of luck. Mission planners do their best within the constraints of limited resources and uncertainty, but history shows that such efforts either succeed or fail. For example, in 2017, when the first interstellar object, named Oumuamua, was discovered, our ability to observe it was quite limited. At that time, we lacked spacecraft capable of observing this mysterious body in detail. All we could obtain were data from telescopes on Earth and in near-Earth orbit. However, this information was insufficient to definitively resolve the nature of this unusual object. When we began to understand Comet Borisov, which became the second confirmed interstellar object to pass through our solar system in 2019, scientists gained a unique opportunity to study it over a longer period. Contrary to initial expectations of close encounters and direct investigation, all observations of this cosmic visitor were conducted remotely. That is, we had no means to approach it or establish contact via spacecraft, which significantly complicated the research and limited the volume of data collected. However, this mode of observation allowed us to gather a wealth of valuable information that helps expand our knowledge of interstellar objects. The third confirmed interstellar visitor in our history is an object called 3IATLAS. For the first time in such discoveries, a spacecraft was close enough to potentially supplement remote observations with in situ measurements. This event marked a significant step forward, because although the mission was not of a comprehensive nature specifically designed for detailed study, even a slight proximity of the spacecraft to the object opens up new possibilities for obtaining more accurate data. Of course, this cannot compare to a full-fledged interplanetary mission prepared with years of planning and resources. Such a goal remains out of reach for now. But even this short-term and incomplete contact greatly enhances our knowledge. The results that the Hera and Europa Clipper missions will provide will become a vital legacy for science. Whatever these spacecraft discover or fail to discover, their data will be reflected in scientific publications for many years to come, serving as a foundation for further research. These findings could help develop more precise models, resolve existing debates, or, conversely, reveal new mysteries that complicate our understanding of the nature of interstellar objects. They will determine how we interpret future discoveries and how accurately we can understand what exactly this interstellar visitor, called 3IATLAS, truly is. In the coming days, it will become clear whether the observed anomalies are persistent and reproducible using different measurement methods. If the data obtained by the spacecraft match ground-based observations and confirm the presence of strange phenomena, then confidence in these features will significantly increase. In that case, we can consider that we are truly encountering real characteristics of this object, rather than random errors or measurement artifacts. However, if the results of the space missions contradict or do not align with ground observations, a thorough investigation into the causes will be necessary. Perhaps the issue lies in incorrect calibration of instruments or in modeling peculiarities. In any case, even such situations will contribute valuable insights to scientific progress. They will help us understand how adequate our current methods and models are for studying interstellar objects. All the results obtained, regardless of their nature, will hold scientific value. Each new discovery, each new hypothesis will expand our understanding of the nature of this unique object. Ultimately, all observations, experiments, and analyses will bring us closer to answering the main question: what exactly is this interstellar guest called 3IATLAS? For now, we await the results of the flyby, and within these expectations, there is hope for new discoveries that could potentially change our perceptions of the universe and how interstellar bodies interact with our world. But beyond that, the story with this object is not yet over. It encompasses many aspects beyond a simple astronomical mystery. The anomalies detected during observations are not limited to just a sun-directed jet emission, an unusual chemical composition of nickel, or rhythmic pulsations. Part 20 of 58. When people start systematically cataloging all strange phenomena, all unusual details, and all observations that do not fully fit into existing models, a complex picture begins to emerge. Gradually, it becomes clear that this interstellar object is a true treasure for scientists seeking anomalies and mysteries. After all, it is not alone, and it raises so many questions for a reason. These are not just one or two peculiarities, but an entire series, at least 15 of them. The material presented seems to reveal a complex and intricate picture of the unusual characteristics of this cosmic object, where each anomaly indicates the presence of unique processes and conditions during its formation, different from those typical for known bodies in our solar system. Let's start with the first feature that sparks particular interest. It appears that the material emanating from the core of this object seems to lose efficiency during its movement, or perhaps its rate of formation and escape beyond the coma is significantly lower than one might expect based on the brightness and luminosity of the coma. In other words, the material leaving the core not only is not being carried away with the expected force into the tail, but its velocity also appears to be lower than it should be under normal conditions. This creates the impression that something is hindering or slowing down its movement, which in itself is unusual and warrants further investigation. Moving on to the second anomaly, known as anomaly number 2. It concerns the so-called jet directed straight toward the Sun, which was discussed in quite detail in our previous discussions. This jet stream, moving toward the central star, despite the usual pressure of solar radiation and solar wind, not only surprises with its direction but also challenges our standard understanding of comet behavior. Typically, such material emanating from the core is pushed away by solar wind and radiation, forming tails directed away from the Sun. However, in this case, there is a phenomenon where some of the matter or energy moves counter to the solar radiation, indicating a fundamental violation of the usual laws governing such bodies. This behavior makes the object particularly intriguing for scientists, as it suggests the presence of unique conditions or mechanisms controlling its activity and structure. The third anomaly is an extraordinary ratio of metal content, specifically a high level of nickel combined with a low iron content, which we mentioned earlier. These indicators, extremely outside the normal range, do not conform to standard compositions of solar or interstellar matter unless one assumes that this object formed under conditions radically different from typical ones, or in an environment with an unusual chemical nature. Perhaps its origin is linked to unique processes that occurred in a distant epoch or in special regions of space where the chemical composition was different from that in the vicinity of the formation of familiar comets. The fourth anomaly is related to the composition of the coma, which is dominated by carbon dioxide, directly contradicting the common model that states most comets are rich in water. An especially bright example of this is comet 3IATLAS, which overturns established notions by showing that its carbon dioxide content exceeds its water content by 8 times. This suggests that the formation process of this comet took place in a very cold environment rich in carbon, possibly under conditions different from those typical of the solar system's birth site. It is quite likely that it formed near another star or within a molecular cloud with a chemical composition significantly different from the usual conditions under which our native planetary system was formed. The fifth anomaly involves the suppression of water content relative to carbon dioxide, essentially a reiteration of the previous point but with a stronger emphasis. It indicates that the water, which normally predominates in ices and cometary particles, appears unusually depleted or trapped within its structure. This fact is crucial for understanding where and how this celestial object formed, as well as for reconstructing its thermal history. It is possible that its formation occurred under conditions so cold that water could not evaporate freely or form icy layers, or that it was transformed into other chemical compounds and preserved in forms inaccessible to observation. Thus, this fact opens a window into the past, allowing us to hypothesize that the conditions of anomaly 10 involve a special structure known as an anti-tail or a narrow jet extension, observed sunward in early images taken by the Hubble Space Telescope. At that time, even before the striking image showing a pronounced and detailed picture of this phenomenon was obtained, observers noticed a faint, thin structure directed toward the Sun in the images. It could have been perceived as a blurry patch, noise, or a random dust trail, which sometimes appears in images of cosmic objects. However, looking back and analyzing these early signals, it becomes clear that they could have served as a kind of warning sign of an upcoming detection of a more complex anomaly, later named Anomaly 2. As for Anomaly 11, it is associated with early signs of water and hydroxide emissions in the distant regions of the comet away from the Sun. Surprisingly, scientists recorded water and O emissions when the comet was only a few astronomical units from the Sun. This distance is much greater than the typical range at which water ice activity is expected, capable of sublimating and releasing gas flows. Such an early water release suggests either that the comet's surface has an unusually exposed and volatile rich icy crust, or that the sublimation process is activated by some other heat source not directly related to solar radiation. It is possible that the comet's structure contains internal heat sources or unique layered formations that trigger such activity. Anomaly 12 manifested as a change in the comet's color to a greenish hue during the lunar eclipse. Usually, comets turn green due to emission from molecules like C2, which glow in the visible spectrum when excited. However, it is interesting that 3 different comets, all named Atlas, exhibited a greenish tint even with very low concentrations of C2 molecules, according to spectroscopic studies. During the lunar eclipse, when Earth's shadow crossed the comet's path and the illumination geometry changed significantly, an unusual color shift was observed. This suggests that the scattering or emission properties of the comet changed in unexpected ways, indicating complex and not yet fully understood mechanisms of interaction between sunlight, the environment, and the comet's composition. As for anomaly 13, it is associated with the detection of hydrogen cyanide, HCN, emission at a heliocentric distance of about 2.13 of an astronomical unit. This chemical component was identified through spectroscopic methods, and its presence became an important fact for understanding the comet's chemical makeup. Interestingly, the ratio between HCN and CN, two related molecules, was found to be similar to that in other comets within the solar system. This indicates that some chemical processes occurring in interstellar and interplanetary environments remain relatively stable and universal. However, the presence of hydrogen cyanide adds an additional layer of complexity to the comet's chemical inventory, especially considering that cyanide compounds are widely used in industrial technologies on Earth, which piques the interest of scientists and engineers. Anomaly 14 is associated with abrupt changes in the ratio of nickel to iron as the comet approaches the Sun, i.e., as the heliocentric distance decreases. Specifically, iron emission was observed only when the comet crossed approximately 2.6 astronomical units from the Sun. Before reaching this threshold, the comet's composition was dominated solely by a nickel-rich volatile fraction, which showed no significant signs of iron presence. After the comet crossed the established boundary, iron began to manifest, indicating its release from internal reservoirs or layered structures. In modern scientific research aimed at obtaining high-resolution images from spacecraft orbiting other planets, experiments are underway that could open new horizons in our understanding of the universe. For example, one such large-scale project is being carried out onboard NASA's Martian Reconnaissance Orbiter. Its goal is to create detailed, high-resolution images of the Martian surface, allowing scientists to study the terrain, geological composition, and possible signs of ancient water processes more accurately. However, interest in these missions extends beyond just the Martian surface. During data processing, opportunities arise to detect and record unusual cosmic objects, among which a passing comet could be included. Such cases attract particular attention from specialists, as they may become the beginning of new hypotheses and theories about the nature and behavior of interstellar bodies. Sometimes, delays in publishing or processing images seem to be related to bureaucratic reasons, perhaps due to the need for additional verification or assessment of the obtained data, or possibly due to the priorities of the mission itself. The time spent on processing adds a certain atmosphere of mystery, creating the impression that these images conceal some special information or important details that require careful study before they are made available to the public. This element of uncertainty enhances interest and prompts reflections on what exactly is happening behind the scenes. Each of these unusual findings, when considered individually, can be explained by various reasons. For example, strange properties of dust found on the surface are not necessarily supernatural or mysterious. It is possible that the formation of these particles is related to the unique environment in which they formed or to the peculiarities of observed artifacts, influenced by the specifics of imaging or data processing methods. It is quite likely that delays in processing and publication are due to technical aspects, such as the features of analysis algorithms, which can cause distortions or artifacts in the images. Anomalous properties of the surface or atmosphere, which seem unusual, could very well be the result of local environmental conditions or processes occurring in interstellar regions. However, when such anomalies begin to accumulate, reaching 15 cases, the situation takes on a different tone. In the observer's eyes, scenes filled with inconsistencies and contradictions start to form, as if patterns that do not fit into familiar models are appearing one after another. Then, an involuntary question arises: perhaps our standard comet model, based on studying samples formed within our solar system, is simply incapable of fully describing interstellar visitors? Maybe objects that formed around other stars, existing in radically different radiation environments and composed of ice and dust with a different primary chemical makeup, behave differently from the comets we are accustomed to. Is it reasonable to assume that the rules and laws we derived from studying comets formed in our solar system do not entirely apply to these interstellar travelers? Or perhaps we are observing something that does not fit within the framework of familiar nature, something more akin to noise, a whisper in the depths of a room, a hint hidden in the dark corners of space. These hypotheses, often sounding like marginal theories or fantasies, are not widely accepted because it seems their authors risk venturing into speculation and unverified hypotheses. However, despite this, a stream of data continues to flow, often raising more questions than answers. And the more we study them, the clearer it becomes that some observed facts evoke confusion and doubt about whether we truly understand everything correctly. For example, there are accumulating indicators that are difficult to explain from the perspective of conventional scientific theories. Nickel compounds without signs of iron, unusual cyanide compounds, rhythmically repeating impulses, and streams. These compounds allow precise control over the nickel layer deposition process, ensuring uniformity and quality of the coating. If it becomes necessary to coat a structure with nickel to enhance its durability or protection, it will inevitably require working in special baths containing nickel cyanide solutions. However, over time, especially when exposed to the harsh conditions of space, such coatings begin to degrade. The effects of ultraviolet radiation, cyclic temperature changes, and mechanical impacts from micrometeoroid particles gradually thin and damage the nickel-rich surface layers. When these layers break down, nickel atoms are released into the environment, and potentially cyanide compounds, which are highly toxic, may also be emitted. Imagine a hypothetical structure coated with nickel, embedded in or attached to a comet's nucleus. As such a comet approaches the Sun and begins to heat up intensively, its icy shell sublimates, that is, transitions from a solid to a gaseous state, releasing gas and dust into the surrounding space. If the structure is partially exposed, its surface, when heated, also starts to emit its remaining volatile components. At this point, decomposition processes of residual materials occur, and emissions of nickel, cyanides, and, depending on the chemical nature of the materials, various carbon-containing molecules can be detected in the gas environment. The detection of such emissions indicates that the comet contains not only natural components, such as ordinary ice or dust, but also decomposition products of artificial materials created by humans or with their technology. This explains the high ratios of nickel and iron observed in some cases. If the structure was made from an alloy with a high nickel content and minimal iron, it could account for the presence of hydrogen cyanide, a toxic gas formed under certain conditions. When cyanide chemistry is involved in material production or surface treatment, such compounds could become part of the surface composition and later be released under space conditions. These processes can also explain the predominance of carbon dioxide in the gases emitted from the comet. If the structure contained carbon-based components, such as polymers, organic coatings, or other carbon-containing materials, ultraviolet radiation and increased temperatures would cause these substances to decompose, releasing carbon dioxide. In this context, the unusually regular 4-hour cycle of emissions can be explained by the presence of ventilation holes, valves, or specialized structural elements within the structure that regulate the gas flow. Perhaps these elements deteriorated over time or from some other cause. After the air inside the system was released into the surrounding space, the pressure instantly dropped. This process created conditions for the next stage, refilling the volume, which in turn led to the cycle repeating. The characteristic timescale for this system was approximately 4 hours, determined by a combination of factors: the size of the compartment, the sublimation rate of the substances, and the airflow resistance through the ventilation opening. This interval was crucial for understanding how the system functions, as it reflected the dynamics of the processes occurring within it. Regarding the Sunwood jet aircraft, its mysterious nature becomes clearer if we assume that its driving force is not related to some random sublimation phenomenon. Imagine that this device is equipped with a specially designed ventilation opening or nozzle oriented toward the sun. Depending on the position or orientation of the object, this opening could be directed so that the gas exiting through it forms a jet aimed at the sun, regardless of where the light source, i.e., the sun, is located. Such a mechanism would allow the device to generate reactive thrust that does not counteract solar radiation but rather bypasses standard solar wind effects. It could release energy from a specific node of the structure with enough force to overcome the influence of solar wind and particle streams. All of this sounds as convincing as it does when you start contemplating this direction. However, to understand the true nature of this hypothesis, one must honestly evaluate all its requirements. In particular, to realize such a scenario, an advanced civilization would need to create a special probe or another space object. This object would have to be in interstellar space, that is, beyond the boundaries of our solar system. Moreover, it could accidentally pass through our system, and as a result, its structure and condition would be such that it would begin emitting signatures that attract the interest of researchers. It is also important to emphasize that its construction does not necessarily have to appear explicitly artificial. It could simply have undergone certain degradation processes that made it more noticeable, but without excluding the possibility that it is the result of natural processes. This multitude of coincidences and assumptions creates the impression that the hypothesis of its artificial origin seems very plausible once you start thinking along these lines. Nevertheless, we must be as honest and critical as possible regarding what this hypothesis requires. In particular, confirming such a theory would necessitate that the relevant space object was built and launched precisely by an advanced civilization and subsequently ended up in interstellar space. This means that he accidentally crossed the boundary of our system, flying through interstellar space, and in the process, underwent degradation that would allow him to emit detectable signatures. All of this is a lot of coincidences, and in reality, the probability of such a scenario seems quite low. Despite all of the above, it is important to remember that we often misinterpret or underestimate natural explanations that could account for the same observations. There is a special term in the scientific community for such situations, the principle that extraordinary claims require extraordinary evidence. It is often attributed to Carl Sagan, and its essence is that the more unusual and bold a hypothesis sounds, the higher the evidentiary standards should be for its confirmation. The claim that 3 objects resembling comets have an unusual chemical composition is, in essence, a modest statement that does not require overly strong evidence. Meanwhile, the hypothesis that one of these objects is partially artificial is much more extraordinary. It implies that very serious and convincing evidence must be provided to support this idea. The question is, do we have such evidence today? The honest answer is no. We only have intriguing anomalies, observed patterns, and a lack of fully natural mechanisms that can explain them. However, this does not mean that dismissing these hypotheses entirely would be correct, since the scientific approach involves continuous development and testing of ideas. Science advances because it does not simply accept ideas on faith but investigates them thoroughly, experiments, and seeks confirmation or refutation. In the case of the hypothesis about the creation of an artificial alloy or material similar to what could be found in space, there is a possibility of verification in principle. For example, if spacecraft passing by a planet or its vicinity detected particles or ions with isotopic ratios that do not match those produced by natural nucleosynthesis processes, this would serve as irrefutable evidence of artificial origin. Such findings could serve as compelling arguments in favor of the hypothesis that there are man-made elements or structures in space. Moreover, if images obtained from orbital satellites or space stations revealed geometric shapes, clear straight lines, or regular patterns that are clearly not found in natural debris, this would also be a strong basis for further investigation. After all, natural stones, debris, or meteorites are generally characterized by randomness and do not contain perfectly symmetrical or repetitive structures. Similarly, spectroscopic studies could detect molecules or compounds that exist exclusively in industrial or technological processes and cannot form naturally under normal conditions. If such molecules were found, it would cast doubt on the natural origin of the materials and might indicate the presence of artificial technologies. At the same time, if future observations revealed natural mechanisms capable of explaining the dominance of nickel in the samples, or if it was found that the excess carbon dioxide on the planet is due to natural processes rather than artificial interventions, and if it was established that the sun emits light without the aid of artificial energy sources and materials, then hypotheses about extraterrestrial or artificial origins would lose their relevance. In that case, according to Occam's razor, the simplest explanation, natural processes, would become the most probable. To date, we have not yet reached this definitive understanding, and the situation remains quite ambiguous. We are in an intermediate phase where data from space are distorted or appear strange, provoking surprise and interest, but are still insufficiently precise or specific to draw final conclusions. This moment is particularly exciting because it is not just idle speculation. We stand on the verge of receiving new, important data that could fundamentally change our perceptions. The results of future observations or spacecraft flybys will either strengthen existing arguments in favor of exotic hypotheses or, conversely, dismiss them, confirming natural causes for the observed phenomena. Until these data arrive, the entire situation remains particularly acute and significant. But at the same time, there is another layer, another aspect to this story that adds extra depth and mystery. Sometimes, what is hidden plays no less a role than what is visible. In the case of the 3IATLAS project, there are missing parts, hidden images, and unexplained delays that only heighten the sense of intrigue and mystery. These details create an atmosphere of uncertainty and raise even more questions than answers. Part 8. Missing data and the Mars Orbiter spacecraft. Silence. Sometimes, what remains unseen or hidden speaks much louder than any words or images. In an era of instant information exchange, when astronomical discoveries are published on social media within hours, and preprint servers are filled with fresh articles and studies, the absence of expected data itself becomes a significant warning sign. In early October, 3IATLAS spacecraft passed relatively close to Mars, so close that several orbital Martian stations would have been able to observe the objects of interest, such as a comet. However, despite such proximity, modern space cameras and telescopes possess such high power and precision that they are capable of distinguishing the tiniest surface details on Mars, even those less than a meter across. This means that if we directed one of these sophisticated instruments, say a space telescope or an orbital spacecraft, at an object located approximately 30 million kilometers away from us, such as a comet hundreds of millions of kilometers from Mars, we would not achieve the resolution necessary for detailed surface study. Nevertheless, we could still record its main characteristics. In particular, such instruments would excellently capture the structure of its coma, the bright envelope surrounding the nucleus, as well as the features of gas and dust jets emanating from it, and the overall morphology of this celestial body, greatly surpassing the capabilities of most ground-based telescopes and observational systems. Of course, it is important to consider that with a comet situated millions of kilometers away, even the most powerful telescope placed in orbit would not achieve the same high resolution as observations from a closer distance. However, even at such a distance, modern spacecraft can provide significantly clearer and more informative images than any ground-based installations because they are closer to the object and are not affected by atmospheric and other interferences that hinder observation. Therefore, the possibility of obtaining images or data about a comet during its passage is quite a realistic scenario, and such observations could very well have taken place. The only question is whether these instruments were indeed aimed in the right direction at the moment the comet passed by. And if they were, then why have we not yet seen published results of such observations? It is important to understand that there are quite ordinary and understandable reasons for delays in publishing the obtained data. Every piece of information received by spacecraft must undergo a complex process of processing and analysis. Initial images require calibration, that is, adjustments and corrections to eliminate errors caused by the instrument's characteristics, as well as to fix possible artifacts that appeared during imaging. After that, the data undergo verification to ensure their reliability and accuracy before becoming available to the broader scientific community or other interested groups. Additionally, the teams managing space stations and platforms have their own priorities and tasks. The primary mission of the orbital spacecraft placed around Mars is to study the planet itself, its surface, atmosphere, geological features, and climate processes. Conducting incidental or even planned observations of comets is not among their main objectives. The time spent obtaining images of the passing comet requires extensive planning, scheduling, and justification of the necessity of such observations. Sometimes, negotiations between different scientific teams and departments are necessary to coordinate priorities and resources. It is likely that such observations were conducted, but their priority was low, and they were probably carried out only in cases of extreme necessity or as part of supplementary research. As a result, the data might still be in the process of processing or analysis, since other, more urgent tasks demanded immediate attention. The factor of geometry cannot be ruled out either. Even if the comet did indeed pass near Mars, this did not automatically mean that the orbiting spacecraft could detect or record it. Orbital mechanics, communication windows with ground stations, and orientation constraints of the spacecraft itself all impose significant limitations on observation capabilities. It is possible that the spacecraft were in unsuitable positions, not configured to track the comet, or that attempts to detect it encountered technical issues. Additionally, it is worth remembering that dust storms on the surface of Mars, while not hindering orbital camera operations, can complicate observations of objects located on or near the surface. However, for cameras mounted on orbital spacecraft, weather conditions on the surface are unlikely to have a significant impact. This raises the question, what if space exploration organizations like HiRes or TGO accidentally captured something entirely unexpected in their images, something that goes beyond usual models and assumptions? In such a case, an instinctive need would arise to conduct a very thorough and in-depth verification of the obtained data before sharing it with the broader scientific community or the public. This caution is driven not only by scientific responsibility but also by historical precedents that highlight the importance of careful handling and interpretation of unusual findings. When anomalies, discrepancies, or signs that suggest these data could challenge existing scientific theories or even become sensational news are discovered, research organizations undertake a special, meticulous verification process. This process involves assembling dedicated observation committees comprising a wide range of experts and conducting numerous additional studies to exclude the possibility of errors or accidental artifacts. Furthermore, alternative explanations for the unusual phenomena are also subjected to detailed analysis to rule out false interpretations or technical malfunctions. Only after a complete understanding of the situation and confidence in the accuracy of the data are they published, and only then when the team of scientists, engineers, and analysts concludes that they either fully comprehend what is happening or, at the very least, have exhausted all possible and logical explanations, even if they do not yet have definitive answers. This process can take months, and in some cases, several years, as it is important not only to technically verify and explain the findings but also to ensure their scientific validity and objectivity. It should be noted that delays in publishing data may have not only scientific reasons but also political or bureaucratic motives. Space agencies are structures managed by governments or intergovernmental organizations, whose activities are often regulated not only by scientific standards but also by public opinion, financial interests, and international agreements. Under these circumstances, if the results of one mission somehow influence the interpretation of data from another or touch upon sensitive topics related to international security or political issues, the process of coordinating and approving information can be prolonged. This is done to avoid unfounded speculation, misunderstandings, and undesirable consequences, as revealing all information without proper preparation could trigger a wave of public interest, panic, or political pressure. Despite the seemingly cynical tone, it is important to understand that these organizations do not operate in a vacuum and are not guided solely by scientific motives. Their activities also involve awareness of public perception, the need to maintain trust and reputation, as well as adherence to internal, sometimes unwritten, rules and interests. There have been cases where some observers, often not entirely fairly, suggested that if satellite images of Mars showed clear evidence of artificial structures or anomalous formations that could lead to a reassessment of the existing ideas about what the third atlas is, these images would most likely be deliberately hidden or suppressed. Such arguments often include the notion that these sensational materials could be classified due to their potential impact, as their publication might cause a wave of public and scientific noise, confuse and disorient the public, and exert pressure on scientists demanding immediate answers and explanations, which they might not yet have. Therefore, it is wiser and safer for everyone to wait until a more complete, comprehensive picture emerges and all lines of evidence converge into a coherent and logical explanation of what is happening. In such cases, it is important to exercise patience and caution, so as not to jump to hasty conclusions, since such assumptions can easily turn into conspiracy theories, which often hinder objective perception of the situation. In reality, to this day, there are no signs that any information regarding Martian research is deliberately being concealed or distorted. There have been no leaks of official documents or testimonies from informants. If the images and photographs obtained through astronomical instruments show a fairly normal situation, that is, a coma without any clearly defined direction or jets pointing directly toward the sun, and without any unusual features, this may raise certain doubts about the reliability and accuracy of ground-based observations of this object. In such a case, if future high-resolution photographs taken from a different vantage point reveal a jet directed straight toward the solar disk at a distinctly different angle, it would serve as convincing confirmation of this phenomenon's existence, leaving no room for doubt or speculation. Similarly, if internal structures within the coma, signs of symmetry, or some form of directed venting are observed in the images, this would provide important clues for constructing and refining our models and hypotheses regarding the behavior and structure of this object. It can be said that such data most likely exist in some form, either stored in observation archives or planned for future research. We are simply waiting for these details to emerge within the framework of official scientific mechanisms, structures, and institutions responsible for space observation and data interpretation. However, the disappearance of images of Mars is not the only strange coincidence associated with the space project or object known as 3IATLAS. At the time when the comet was near perihelion, that is, at its closest approach to our Sun, and exhibited its most unusual behavior, other mysterious events were recorded in both near and distant space. Collectively, these observations form a certain pattern, which may either be a mere coincidence or indicate the existence of a deeper, causal connection occurring within our surrounding cosmic environment. Part 2, about mysterious coincidences in space and objects diving behind the solar disk. And what if all these strange phenomena related to the three-eyed atlas are not isolated or unique? What if they are merely part of a broader pattern, representing the manifestation of some hidden processes? Between October 11 and October 14, 2025, reports emerged of 4 different objects moving along a near-Sun orbit, that is, heading toward our star. These objects, tracked by solar observatories and telescopes, apparently originate from roughly the same region of the sky as the mysterious 3IATLAS. They head toward the Sun. Some of them seem to disintegrate into pieces, while others vanish in the bright sunlight, as if dissolving into its radiance. Such near-Sun comets are not an uncommon phenomenon. The Kreutz family of comets, a group of objects believed to be fragments of a larger, ancient body that disintegrated several centuries ago, regularly sends its members toward the solar disk. Every year, solar observatories record dozens of such comets, which gradually evaporate under the intense heat and radiation of the Sun, transforming into a hazy cloud of dust and gas. However, what is particularly intriguing is that exactly such a cluster of events occurred during these days. 4 objects in 4 days, all originating from the same direction, coinciding with the period when the 3IATLAS exhibited its most unusual and mysterious behavior, with its approach to perihelion reaching its peak. Can this be considered a coincidence? Probably, since the sky is vast, and the space around the Sun constantly intersects with numerous small bodies hidden beyond the visible horizon. Modern observational capabilities, especially with advanced space-based solar telescopes and specialized instruments, allow us to detect and record more such objects than ever before. Statistically, discovering 4 such events in a short period is not impossible. Rather, it is a normal consequence of active periods and the expansion of our observational reach. However, when such objects begin to converge, if we consider a situation where three separate atlases containing information about the eyes, or rather their fragments, were lost or became inaccessible several months or even years ago, it can be hypothesized that the orbits of these fragments might have slightly differed from the orbit of the main core to which they were initially attached. As a result, these differences in trajectories could have led to these debris reaching perihelion, the closest point to the Sun, at different times. This effect is well known not only theoretically but also in practice. It has been observed in other comets. For example, it is well known that comet Shoemaker-Levy 9, which disintegrated into multiple fragments during its approach to Jupiter, forming a chain of pearls. These shards, with different orbits, were tracked and recorded by scientists. Subsequently, they fell to Earth over several days, creating an effect reminiscent of a chain, as if adorning the sky with numerous precious stones. In the case of our hypothetical objects, spectroscopic analysis of those heading toward the Sun could help test this hypothesis. If their chemical composition matches an unusual one, differing from standard cometary materials, this would be a strong argument in favor of their kinship with the first three atlases. In that case, we could speak of a certain connection. However, if spectroscopic studies show that their chemistry corresponds to the typical composition of cometary bodies, then these objects are most likely unrelated and do not share a common origin. It is worth noting, though, that obtaining detailed spectra of such objects is a very challenging and labor-intensive task. They are usually very faint, move at significant speeds, and their appearance on the screen is brief. Special instruments, coronagraphs or coronographic displays, are used to detect and analyze them, as they allow capturing the faint environment surrounding bright solar radiation. However, images obtained with such devices often lack spectral information that could help determine the nature of these objects. At the same time, another event occurred that attracted widespread public attention, although it was quite difficult to assess it with absolute certainty. During the launch of a spacecraft created by SpaceX, named Starship, observers analyzing footage of this launch against the backdrop of the Moon noticed something unusual. A bright point of light appeared in the frame, located near the lunar glare, a luminous spot that seemed to hover for several seconds at a specific point, completely inconsistent with the orbits of known satellites, stars, or planets. Afterward, it disappeared. This event sparked a flurry of speculation on the internet. People began discussing what it could have been: a real object, a spacecraft, debris, or perhaps an optical artifact caused by the camera or optics. Flare and reflections inside the lens are quite common in astrophotography, especially when bright light sources like the Moon are present in the frame. Light within the system can scatter across lenses, reflect off sensor surfaces or other optical elements, creating false images that appear as bright spots, streaks, or sparks. To determine whether this spot was a real object or merely an optical artifact, a thorough analysis of the original footage is necessary. It is important to understand the operation of the camera used, its characteristics, and to compare the footage with images obtained from several independent devices. Only with such confirmations can we speak of the presence of a genuine object in the frame. In this case, such an analysis was either absent or insufficiently convincing and was not published in open sources. It should be considered that the bright point could have been anything: an actual space object, a satellite, or even a meteor that briefly entered the camera's field of view. But with equal probability, and sometimes even greater, it could have been just an optical artifact. Interestingly, humans, these remarkable creatures by nature, are essentially complex pattern recognition machines. Our brain has an exceptional ability to find and establish connections even where none may actually exist, because in the system of our ancestors, in the era of primitive communities and the first civilizations, false positives in recognition often cost less than false negatives. This meant that our subconscious and analytical abilities were designed to prioritize responses to potential threats or significant events, even if they were mistaken or seemed implausible. As a result, our brain automatically perceives unrelated events and creates sequences or stories that connect them into a whole. This is a natural, albeit sometimes distorted, trait of human thinking. However, it is important to remember that these connections created by our mind do not necessarily correspond to reality and do not always reflect objective relationships between phenomena. Let us pause for a moment and, as if conducting a mental experiment, try to imagine that this idea is not just a hypothesis but a hypothetical hypothesis, quite possible within the framework of physical and astronomical processes. Suppose that at some point in time, a cosmic event or impulse occurred that disrupted the usual state of the interplanetary environment. Such an event could have affected several small bodies within our solar system simultaneously. For example, it could involve the ejection of high-energy particles from the Sun, a strong and unusual coronal mass ejection, or a powerful density wave that suddenly penetrated interplanetary space. Perhaps it was something that disturbed the normal state of the cosmic environment, triggering certain physical reactions in small bodies like comets or asteroids. It is quite possible that such events caused gas release from comets, disturbed their stability, or even affected their orbits, resulting in some short-term but noticeable optical phenomena. The question of the physical nature of this process and its mechanisms is indeed complex, and fully explaining it is no simple task. However, in principle, ruling out such a possibility is not justified. After all, coronal mass ejections are powerful eruptions of plasma and magnetic fields originating from the Sun. These ejections propagate throughout the system at high speed and can cause a variety of consequences. When such powerful ejections encounter Earth, they trigger geomagnetic storms, produce auroras, and disrupt satellite systems and power grids. But if we consider their influence on other objects, such as comets, the situation becomes even more intriguing. Interaction between coronal mass ejections and comets can lead to their compression or enhancement of ion tails, as well as trigger gas or dust outbursts, which in turn may cause short-term optical flashes or anomalies in observations. Therefore, if a particularly powerful or unusual coronal mass ejection had occurred at the beginning or middle of October, it could have affected not only Earth but also other bodies in our interplanetary space. Among them are three objects known as the 3IATLASes. They might have been subjected to such solar impulses, which could explain their unusual behavior during this period. Modern solar observatories continuously monitor the Sun and record any significant manifestations of its activity. A quick review of the relevant reports for October could help determine whether major coronal mass ejections or solar flares coincided with the observed anomalies. If such events took place, they could be considered a possible cause of the observed phenomena. If not, then it is likely that only coincidences, timing alignments without causal connection, remain to be explained. Objects disappearing behind the Sun, the bright point where the starship was located, and the unusual behavior of the 3IATLASes, Part 10. The motif of change, expressed in the behavior of cosmic visitors to our solar system. Many may believe that the 3IATLASes are unique and exceptional representatives of their kind. However, scientific observation shows that they may follow certain patterns that are only now beginning to become increasingly apparent to specialists. This behavioral model, or rather trend, indicates that objects arriving from interstellar space are starting to challenge our usual perceptions of them, as well as how they should behave within our system. It all began in October 2017, when the first interstellar object, designated I-UMOA, was discovered, something that became the first confirmed case of an object passing through our planetary system originating from beyond the solar system. This object generated great interest and intrigued scientists because its behavior and characteristics immediately stood out against the background of previously known objects. UMOA, as it was called, differed from all known bodies and appeared quite unusual from the very beginning. Its appearance and features did not indicate the presence of a prominent coma or tail, nor clear signs of gas emission, despite passing very close to the Sun. Typically, at such proximity to our star, water ice and other volatiles should have rapidly sublimated, transforming from solid to gas, creating a visible atmosphere around the object. However, nothing of the sort was observed with UMOA. Due to the lack of signs of activity and coma, it was immediately classified as an asteroid, a solid body showing no signs of cometary activity. But in fact, its trajectory suggested the opposite. Astronomers noticed that as it moved along its orbit, it slightly accelerated away from the Sun, and this acceleration could not be explained by gravitational forces alone. Something seemed to be pushing this object, giving it additional speed. For comets, such non-gravitational acceleration is quite common and well understood. In the case of a comet, the release of gas and dust creates an effect similar to a rocket. Material ejected in jets from the side illuminated by the Sun acts as a thrust, pushing the nucleus in the opposite direction. This effect can explain the comet's acceleration, provided it releases visible gas and dust. But Oumuamua emitted neither coma nor jets, nor any other visible gas. Nevertheless, it continued to accelerate, as if something or someone was pushing it, and this became a real puzzle. More and more hypotheses emerge. Perhaps it was emitting some faint substance, like hydrogen, which, despite being invisible, could provide a small thrust. Or maybe it was affected by unusual pressure from solar radiation, a phenomenon similar to a solar sail, a thin film of light creating a force of thrust. Or perhaps it involved some exotic material, such as solid hydrogen ice, which is so fragile and sublimating that its emission was invisible to observers. Each of these options had its drawbacks and required assumptions beyond conventional scientific understanding. All this made the mystery particularly complex. Additionally, an important aspect was its external structure. Observations showed that the object was extremely elongated, about 10 times longer than it was wide, and had a cigar or even disc-like shape. No asteroid or comet known in our solar system possessed such a form. This added to the mystery, making the object even more unusual and sparking lively debates among scientists. Intense discussions erupted in scientific circles. Some insisted that all of this was the result of natural processes, albeit very exotic ones, while others suggested that something more mysterious was at play. A special place in these debates was occupied by hypotheses about possible artificial origin. This interstellar comet made an impression with its external resemblance to familiar cosmic objects. Its coma, bright and well-defined, indicated active gas emission around the nucleus. The spectrum of this body contained familiar molecules such as water and carbon monoxide, those same substances commonly found in comets orbiting within our solar system. The relative proportions of these substances suggested that its chemical composition was quite typical, and the overall behavior of the object was quite ordinary and calm. Researchers assert that these interstellar visitors, despite their origin beyond our solar system, may be nothing more than standard celestial bodies, indistinguishable from those we observe within the solar system. In particular, Borisov, one of the leading astronomers, confirmed that not every object beyond our star system must automatically violate known behavioral rules. He emphasized that it was indeed a comet, and its behavior aligned with all familiar scenarios. Although the hypothesis of an interstellar origin for this body was, without a doubt, unusual and attracted significant attention, it turned out that its nature is quite standard, which brings a certain reassuring calm. At the same time, our collection of observations has revealed 3 different interstellar objects, each demonstrating its own unique, sometimes strange, nature. These 3 objects, so-called ATLAS, are returning to us with doubled force and raising even more questions. If one of them, tentatively called Oumuamua, seemed unusual only because it did not exhibit the expected characteristics, the others, such as the 3 atlases, appear strange precisely because they display behavior that contradicts our usual understanding. For example, one of them moves along a trajectory where, according to the laws, an anti-solar tail should be observed, but it is absent. Its composition includes nickel and carbon dioxide, while iron is completely missing, and water seems to be suppressed by carbon dioxide. Majestic rhythms reminiscent of a mechanical heartbeat are also a feature that emphasizes its cometary nature. However, it behaves as if it were a comet that, having read the textbook backwards, defies all conventional notions. If we attempt to establish a chronological order of these 3 interstellar visitors, a certain pattern becomes evident. The first object exhibited unusual activity in regions where, according to our expectations, silence should have prevailed, and it also possessed a mysterious acceleration. The second is an object with a quite ordinary, balanced chemical composition, demonstrating calmness and predictability. The third is a mystery that surprises with its reverse activity and strange chemistry, as if the universe decided to test our ability to recognize the unusual. According to scientists, this combination resembles a demonstration of successive stages, allowing us to understand how the universe tests our perception and reaction to anomalies. Or perhaps these observations are a lesson showing that our classifications, comets, asteroids, or interstellar visitors, are too rigid and based only on limited and selective experience drawn solely from our solar system. The key question here remains, are these objects just random outliers, rare exceptions, statistical anomalies that attract our attention precisely because they are unusual? Perhaps most interstellar bodies are quite standard, weakly manifested objects that go unnoticed because they are too small or their chemical composition is too ordinary to be detected at early stages. Alternatively, these three strange visitors might be just the first representatives of a much larger and more diverse population of entities, countless and far from the conditions of our solar system. These objects could have formed under unique circumstances. Such unusual objects can be compared to astronomical analogues of two-headed calves, rare congenital defects or strange accidental circumstances that do not reflect the general picture among stellar systems and cosmic bodies. They are exceptions to the rule, uncharacteristic of most objects, and despite their rarity, they inspire scientists with a genuine desire to understand their nature. At the same time, we are not inclined to use such rare cases to rethink or rewrite the entire body of knowledge, since these deviations are more likely exceptions rather than the rule. The inversion effect, this tendency in observing interstellar objects that distorts our expectations, may indicate something deeper and more significant. It suggests that the galaxy and its diversity are not limited to standard scenarios. Star formation occurs under very different conditions, and each case is a separate story. Some stars form in dense clusters where interactions of radiation and gravity are so intense that they create unique situations. Others are born in isolation, in sparse outer regions of molecular clouds, where conditions for their formation differ significantly. Moreover, it is important to consider that the composition of gas and dust in these regions varies depending on their metallicity, that is, the content of heavy elements. In metal-rich areas, the history of previous supernovae and the presence of nearby massive stars enrich the surrounding material, influencing the properties of forming objects. The chemical composition of comets forming around stars in such metal-rich regions can differ from that of comets born in less metal-rich areas. For example, comets forming near massive stars sometimes exhibit more intense radiation, which in turn affects their surfaces. They change, become more noticeable, or certain volatile substances are displaced, altering the properties and structure of the comets. Of particular interest are the three so-called atlases. These objects with a predominance of carbon dioxide and unusual metals, which can be explained as products of the unique conditions of their formation in exotic parts of the universe. Perhaps their formation occurred near carbon stars, types of stars in whose outer layers the amount of carbon exceeds that of oxygen, leading to the formation of carbon dust and unique chemistry. There is also a possibility that these objects spent part of their lives in dense molecular clouds, where cosmic rays processed the ice in unusual ways, resulting in distinctive chemical and physical properties. It can also be assumed that some of them are very ancient bodies, billions of years old, whose surfaces have been subjected over time to prolonged exposure to the interstellar radiation field, which could have contributed to their unusual appearance. All these explanations are quite natural and logical. They help to understand the peculiarities of these objects without resorting to hypotheses of extraterrestrial interference or artificial origin. However, deep down, we are also attracted to a more speculative version. If interstellar space is occasionally crossed by probes or artifacts of other intelligent civilizations, then such objects undoubtedly challenge our usual notions of the nature of the cosmos. They were not created by natural processes but were selected and engineered, made from materials chosen deliberately rather than randomly. Objects created by intelligent beings could have specially designed systems functioning rhythmically or purposefully, setting them apart from natural bodies. Their structures might possess systems capable of performing specific tasks, rather than accumulating mass or forming chaotically by chance. Perhaps they have mechanisms operating with a certain rhythm or systems intended for particular purposes. All of this points to conscious design. In this context, any unusual turn of events or any object that defies our conventional understanding of the universe is not a coincidence but a kind of signature. It may indicate activity by those who created it. While humanity continues to try to unravel the endless mysteries of space, it is worth paying special attention to the fact that the year 2025 has become a year of significant discoveries and new horizons capable of fundamentally changing established ideas in various fields of science. These achievements also make a substantial contribution to the development of cosmology and astronomy, sparking active discussions and challenging many long-held dogmas. One of the most striking examples of such groundbreaking discoveries is the project called 3IATLAS. It is important to emphasize that this project does not exist in isolation. It is part of a broader scientific picture unfolding in an era when science encounters new, sometimes astonishing factors and phenomena. During this same period, the fundamental assumptions underlying our knowledge of the cosmos are being tested and revised. The time when dark stars baffle scientists, when artificial intelligence uncovers patterns in physical processes previously unnoticed or inaccessible to human perception, and when achievements in quantum teleportation reach boundaries that seemed unattainable just recently, all of this is creating a new era of scientific discovery. At the same time, the energy obtained from thermonuclear fusion is ready to cross thresholds capable of fundamentally changing the technological fabric of civilization. Perhaps we have entered an age when anomalies and unusual phenomena become commonplace, and the universe itself begins to demonstrate complexities that previously seemed impossible, at every level of its study and understanding. Part 11. The focus is on mysterious dark stars, which provoke heated debates among scientists. Recent results obtained with the James Webb Space Telescope, as well as data from other modern studies, have led to an unexpected and sometimes contradictory discussion about the order and sequence of the formation of the first structures in the universe. According to the classical and most widely accepted scientific model, the development of the cosmos followed a certain logic. Galaxies first formed from small density fluctuations in the early universe, which was extremely uniform and cold. These fluctuations led to the concentration of matter at specific points, where galaxy cores later formed, and within them, black holes, created through the accumulation and collapse of matter. This sequence was considered logical and well calculated. Initially, gas condensed into stars. These stars grouped into galaxies, and at their centers, enough mass accumulated to produce supermassive black holes. This scenario fit well into the bottom-up concept, where complex structures arise from simpler, smaller elements, building into a unified whole. However, the results obtained with the James Webb Telescope challenge this orderly picture. Scientists have discovered supermassive black holes, with masses exceeding millions and even billions of times that of our Sun, existing at a time when the universe was less than 1 billion years old. This fact causes surprise and bewilderment. Such black holes should have grown through accretion of matter and mergers in a relatively short period, yet their formation appears to require much more time than they currently have. Therefore, two possible explanations emerge. Either these black holes were initially much larger than current theories predict, or they grew at an astonishing rate that exceeds conventional expectations. There is also a third possibility. Perhaps the very sequence of structure formation was different from what was previously assumed. One of the hypotheses suggests that black holes could have formed even before the appearance of galaxies, at a very early stage of the universe's development, at a time when structures that would later become galactic cores did not yet exist. This idea led to the hypothesis of so-called dark stars, hypothetical objects that could have existed in the early universe. Perhaps our understanding of black holes, some of the most mysterious and impressive cosmic objects, needs to be reconsidered. Maybe they are not as massive as commonly believed, and their true nature is hidden behind the boundaries of modern theories. There are reasons to believe that black holes may multiply faster than previously assumed, which necessitates a revision of our models of their formation and evolution. And perhaps our notions of the early universe, the conditions and processes that were considered established, require more thorough examination and clarification. Nevertheless, the very fact that we are discussing these questions, that we are questioning established cosmological concepts based on reliable observational data, indicates something greater. It reflects significant shifts in our understanding of the structure and development of the cosmos. Our existing models, despite their successes and wealth of observational data, face difficulties and do not always meet our expectations. As a result, we are beginning to realize that the universe is far more complex and astonishing than we could have imagined within narrow theoretical frameworks created for convenience. If we allow for the possibility of errors in understanding such fundamental processes as the sequence of galaxy formation, black holes, and other structures that determine the large-scale architecture of the cosmos, then making mistakes and assumptions about the behavior of interstellar comets or small cosmic objects seems almost insignificant in comparison. In both cases, we base our conclusions on data obtained from limited samples and assume that these data are representative of the entire universe, only to soon discover that there are tricks in it that we had not considered at all. Dark stars, which are discussed within the framework of the three atlases, play an important role because they provide context for understanding the entire picture. We are not living in an era of established science where all important questions already have definitive answers, and scientists merely supplement them with new details. We are in an era when fundamental assumptions about the structure and origin of the cosmos are being questioned in nearly all fields of research. This does not mean that every unusual discovery or anomaly automatically becomes revolutionary. In most cases, such deviations turn out to be the result of measurement errors, calibration failures, or manifestations of effects well understood in theory but unusually expressed under specific conditions. However, among these deviations, there are genuine anomalies confirmed by reliable data that require us to reconsider our theoretical foundations. Some of them are so significant that they force scientists to essentially build new models of the universe from scratch. The three atlases may turn out to be such a case, either dismantling existing theories or serving as a lesson, demonstrating that cosmic chemistry and physics, though sometimes exotic, are also natural and consistent. The main point is that we cannot dismiss these phenomena simply because they contradict our current models, as our theories are clearly incomplete and need to be supplemented or even radically restructured. The universe is not obliged to conform to our expectations and notions, and this is constantly confirmed by experience, especially in the year 25, which repeatedly teaches us humility and openness to new ideas. Part 12. A time when artificial intelligence and fundamental physics stand at a crossroads. In 25, artificial intelligence will cease to be merely a tool assisting scientists in their research. It will become a key factor revealing what humanity has often overlooked. Modern machine learning algorithms, trained on vast amounts of data, are capable of identifying patterns, connections, and even anomalies that would take humans years of painstaking research to discover or might never be found at all. This transforms AI into a powerful instrument that is revolutionizing nearly all fields of science, and astronomy is no exception. Recent scientific works in high-energy physics and cosmology already mention artificial intelligence systems as co-authors. An AI capable of analyzing light curves of variable stars can detect hidden and often imperceptible patterns in the noise, which are not easily noticed through simple visual observation. This unique capability is especially significant in studies of objects like the three atlases, since the spectra, images, and brightness curves we have collected contain far more information than any human researcher can fully recognize and interpret. Within this data set lie the most delicate correlations between stellar composition and activity models, as well as temporal relationships within stellar processes and spatial structures in their surroundings, which can reveal the internal organization of star systems and help us understand the nature of their behavior. An AI, specially trained on numerous comments and observations and then applied to the data obtained from the three atlases, can identify patterns that explain anomalous phenomena or point to additional, previously unnoticed peculiarities. It can detect features that, for some reason, have remained invisible to the human eye, thereby expanding the horizons of our understanding. However, alongside this powerful capability, potential risks must also be considered. Artificial intelligence systems trained on specific datasets may begin to detect and memorize patterns that are not related to the true physical nature of stellar objects, but rather to the peculiarities of the tools and observation methods used. As a result, they may overfit, learning and retaining artifacts caused by technical errors or equipment peculiarities rather than actual physical phenomena. Moreover, such systems can unintentionally reinforce and amplify existing biases embedded in the training data, thereby confirming pre-existing hypotheses and assumptions rather than subjecting them to careful and critical analysis. Imagine an AI trained primarily on data about comets and other solar system objects, which starts identifying all unusual phenomena in 3IATLAS as anomalies simply because these phenomena differ from typical patterns, not because they are physically impossible. A crucial aspect in this context is the skillful combination of pattern recognition capabilities provided by artificial intelligence with human skepticism and intuition based on physical laws and experience. Allow the AI system to scan all observed data for unusual signs and anomalies, while humans thoroughly verify these findings, look for possible artifacts, and develop models to explain what is observed from a physical perspective. This hybrid approach is already successfully applied in gravitational wave astronomy, where AI detects potential signals within detector noise, and scientists evaluate their likelihood of authenticity, distinguishing real gravitational waves from false alarms or technical malfunctions. The same method could become revolutionary in our study of interstellar objects, which manifest in very unexpected and complex ways. Imagine an AI system that processes every observation related to the triple atlas, any spectrum, each image, and each time measurement, searching for hidden links and correlations among them. It might discover that a 4-hour pulse coincides with specific spectral line characteristics, indicating the presence of a chemical cycle or a special energy mechanism. Alternatively, it could become clear that the intensity of the sunwood jet solar stream varies depending on the nickel-to-iron ratio, which would suggest a common driving mechanism controlling this phenomenon. The system could also recognize precursors, subtle changes in a comet's composition hours before outbursts, enabling predictions of future activity and events. Or, conversely, it may fail to detect any patterns, confirming the assumption that anomalies are random, caused by processes that are too complex and chaotic to be recognized. In such a case, even a negative result becomes valuable. The year 2025 marks an important and pivotal stage in the development of modern science, opening new horizons and possibilities for humanity. This year signifies an epochal shift in how we study the world around us, as we begin to actively integrate human intelligence with artificial intelligence, fundamentally changing our understanding of what was previously possible. These new ways of interacting with machines and algorithms allow us to approach the most complex questions from a different perspective, expanding the boundaries of our knowledge. Unlike previous computing tools, modern AI systems have achieved results that once seemed unattainable. Thanks to these innovations, not only does the speed of obtaining answers increase, but the quality of questions we can explore improves, as does the range of tasks that become solvable. When it comes to modern research, such as the project called ATLAS, it becomes clear that within vast datasets, secrets are hidden that were previously inaccessible. In such cases, artificial intelligence can serve as a unique key to unlocking them, opening new horizons for science. And if, during data analysis, AI confirms that the detected anomalies are stable and interconnected, this will provide strong evidence for the existence of unusual or even exotic explanations for the processes occurring, whether natural or otherwise. All of this represents important steps toward a deeper understanding of the structures and patterns of our reality. Among the breakthroughs, the development of quantum teleportation stands out, one of the most astonishing and seemingly fantastical directions in modern physics. In 2025, human imagination and scientific thinking have approached making the impossible practically commonplace. Information that previously seemed inaccessible or required complex and lengthy transmission methods can now move without crossing the space between sender and receiver. This is the essence of quantum teleportation, the instant transfer of quantum states from one place to another, without physical movement of particles or signals through space. It can be said that this is akin to magic, but in reality, it is the result of the most advanced scientific achievements, realized in 2025. Researchers from Northwestern University, together with colleagues from several other institutes, have achieved what only 10 or 15 years ago was merely a dream. They successfully teleported quantum information over standard fiber optic communication lines spanning 62 miles, approximately 80 kilometers, while the equipment operated under conditions fully compatible with existing internet infrastructure, using the same cables that transmit your emails, video streams, and banking transactions. This is not a theoretical hypothesis or fantasy, but a fully realized experimental result. Scientists demonstrated that transmitting quantum states over such distances is possible with an accuracy of over 90%, making it feasible to use this technology for communication between major cities and regions. Just think for a moment, those very fiber optic cables that now carry streaming services like video or movies, as well as millions of transactions and vital medical records, are now capable not only of transmitting conventional information but also quantum states. In a literal sense, reality itself, its fundamental laws, is being transmitted along with the morning news, through the same channels as your favorite movies or work documents. All of this has become possible thanks to mechanisms based on principles of quantum physics, which astonish and simultaneously raise questions among many scientists and specialists because they touch upon the very foundation of our understanding of the universe. At the core of this is a phenomenon known as quantum entanglement, which creates an extremely strong connection between two particles. This connection is so instantaneous and inexplicable from the perspective of classical physics that even the renowned physicist Albert Einstein called it spooky action at a distance. In this phenomenon, two particles become entangled in such a way that this is the key point that helps understand the essence and implications of modern advances in quantum technology. This process, related to the transmission and processing of quantum information, requires calculations of extraordinary precision and strict adherence to timing, as any errors or disruptions can lead to serious consequences. Correcting such errors becomes an extremely challenging task, since every second and even fractions of a second count. Imagine billions of photons passing through a delicate fiber optic cable that serves as the information carrier, each carrying important quantum properties. At the same time, the fiber itself possesses properties hostile to maintaining such sensitive quantum states because it is susceptible to thermal noise, vibrations, and electromagnetic interference. All of this poses a threat to maintaining coherence, the property that allows quantum systems to stay in the desired state. As a result, during passage through the fiber, quantum information can lose its unique nature. This is known as decoherence. Therefore, the task is to protect information from such destructive factors and ensure its transmission with maximum accuracy. To combat this, scientists use advanced filtering methods that minimize the impact of external interference. For example, superconducting detectors cooled to temperatures just above absolute zero are employed, significantly reducing thermal noise and increasing the sensitivity of the instruments. Additionally, active protocols are implemented, based on the simultaneous transmission of both quantum and classical signals. In such systems, classical information essentially serves as instructions that inform the receiver how to manipulate the received quantum states in order to restore them to their original form. This is similar to a situation where a message and the key needed for its decryption are sent simultaneously, except that this key is quantum information, which requires special protection and attention. The distances involved in these experiments and technologies, although small on cosmic scales, are still enormous for quantum systems. For instance, a distance of 46 kilometers is a colossal span, requiring the preservation of quantum coherence without losses or distortions. Remarkably, such tasks are now being solved repeatedly, with experiments being repeated and consistent, stable results achieved. This indicates a transition from laboratory research to practical technologies capable of application in real-world conditions. The advantages of such developments are impressive and open new prospects for long-distance communication in space. Imagine space probes exploring the outer regions of the solar system or even interstellar space. Under normal conditions, radio signals sent from Earth weaken over time, require significant energy to boost and propagate, and travel at the speed of light, taking several hours to cross the entire solar system. For example, data transmission from interplanetary stations like the Voyager probe takes from 4 to 24 minutes, depending on their position in the orbital system. A message sent to Mars reaches the surface in 4 to 6.5 minutes, while a signal from Voyager can take up to 18 hours to reach us. All this happens not because the signals are weak or require enormous power, but because they, like light, travel at a speed that can be considered the finite speed of information propagation. A quantum communication line can create a secure channel with a unique property. Any attempt at interception or interference is immediately detected, as the very act of interference instantly destroys the signal or causes its distortion. Thus, both parties in the communication receive warnings about potential threats, making such a channel virtually impossible to hack or eavesdrop on. Here, security is ensured not by traditional encryption methods, but by fundamental laws of physics that prohibit interception and copying of quantum information without violating its nature. An even more important aspect is that the quantum classical fiber optics, one of the most remarkable achievements of modern science, is designed to transmit light pulses encoded as sequences of ones and zeros. That is, a binary system that underpins the digital language of modern computing technologies. In this process, light traveling through fiber optic cables acts as the carrier of information, and its essence lies in the precise transmission of signals, where each 1 or 0 is an elementary data bit. This approach allows for the transfer of vast amounts of information at high speeds, supporting the operation of global communication networks, the Internet, and many other systems upon which modern life depends. However, if we look a bit deeper, we can see that this technology is merely an outer shell, a superficial embodiment of more profound physical phenomena. Quantum fiber optics, in turn, could offer something significantly more fundamental than just the transmission of binary signals. It is capable of carrying not only information encoded as bits but also the very quantum nature of information itself, the pure quantum possibility that exists in nature. Essentially, this represents the difference between two levels of perception. On one hand, the description of a landscape, its characteristics and structures. On the other, being within the landscape itself, experiencing it as a living reality. An analogy can be drawn with reading musical notes and listening to a symphony. One is merely a recording, information about the music, while the other is a genuine experience, immersion in the music, feeling its fullness and depth. In this sense, quantum optics could become a means not only for transmitting information but also for conveying the very quantum essence of reality, which is not just a message about the world but its direct embodiment, transferred without distortion from one place to another. Let's now consider an example, a comet atlas named 3IATLAS. What if, in the distant future, at a very promising stage of technological development, humanity manages to send space probes equipped with quantum sensors designed to intercept and study such cosmic objects? These probes, capable of instant response, would require protected and uniquely reliable communication channels that cannot be hacked or intercepted by third parties. Additionally, they would need a distributed computing system capable of analyzing large datasets in real time, detecting anomalies, and responding to them without delays. However, the mechanisms that could ensure the creation and operation of such systems are already being tested today. We are building infrastructure for the development of space communication networks, often without fully realizing the scale and importance of this process. In turn, this leads us to a darker and more mysterious hypothesis, linking the mechanics of quantum teleportation with secrets hidden beyond the limits of our understanding, with the mysteries surrounding an object known as 3IATLAS. If quantum communication becomes commonplace and can be used to develop modern engines or to harness new, exotic physical effects, then the question arises, could Atlas itself utilize such technologies? Not necessarily referring to classical quantum teleportation as understood by scientists and experts, but to a mechanism that employs quantum phenomena to transfer matter or energy along unexpected and as yet unknown pathways. There are already observations in nature that pique interest. rhythmic emissions with a chemical composition that does not match what current models predict, as well as jets exhibiting coherence that should not be preserved within such small and cold bodies. All of this seems to hint that on scales where quantum effects become significant, something unusual is occurring, something capable of manipulating the laws of physics. In conditions where classical physics gives way to quantum, phenomena beyond our usual understanding are possible. Stars can primarily be considered objects governed by classical physics. Their structure and behavior are well described by existing theories. Planets, likewise, are mostly understood within this framework. When we carefully and actively examine the three-dimensional atlas, which represents a complex and volumetric map of data, our perception is not limited to passive observation. On the contrary, we engage in active interaction with this atlas, as if participating in a complex game with invisible threads. We do not simply look at it from the outside. We seem to be involved in a process that allows us to understand and record the properties of objects hidden within its structure. At this moment, we perform what is called a collapse of the superposition, a quantum state in which the properties of objects could remain indefinite or exist in multiple potential states simultaneously. As a result of our action, specific characteristics become fixed, which otherwise might remain in an indeterminate state, invisible to our perception, until a particular measurement or observation is made. The year is now 2025, a significant milestone in the development of science and technology, when it becomes clear that we possess the capability to teleport quantum information through existing infrastructure. This discovery overturns our notions of data transmission and information flows. An important question arises: has anything similar happened in space, or have processes akin to this occurred there over extended periods? Perhaps, on the vast scale of the universe, there are objects resembling our three atlases, cosmic quantum computers that manipulate their own states using entanglement and superposition. Such objects seem strange and incredible to us because we perceive only their manifestation, the collapse of potentials into the familiar classical reality. However, this is merely our perspective, conditioned by our perception and limitations. Now, let us move on to a topic that divides the boundary between the possible and the impossible, the point of no return. In this context, we speak of the point of no return, the moment when it becomes impossible to go back, when certain processes acquire an irreversible nature. This point is conditionally called a punctum in the chain of events, after which changes can no longer be undone or halted. In the realm of energy and stellar processes, one of the most vivid examples is our Sun. It has been shining for over 4,600,000,000 years, continuously converting hydrogen into helium through nuclear reactions occurring inside its bright core. At this moment, it releases an incredible amount of energy, more than 7 trillion times the energy humanity has used throughout its entire history since the emergence of the first civilizations. Every photon, every spark of light warming your face on a sunny day, is the result of a unique and extraordinary thermonuclear fusion process. Thanks to these reactions, photosynthesis occurs, allowing plants to convert sunlight into energy that sustains all life on Earth. Additionally, the energy released during these reactions governs our climate, influences weather, shapes ocean currents, and supports life in all its forms. The study of phenomena related to thermonuclear fusion has been ongoing for over 100 years. Scientists persistently and patiently strive to understand and master this process so that one day they can reproduce it on Earth under controlled conditions. However, until recently, all their efforts were unsuccessful. Despite tremendous advances in knowledge and technology, scientists had not managed to achieve a reaction with a positive energy balance. That is, producing more energy than was invested in initiating and sustaining the process. This task seemed impossible, seemingly beyond the reach of human capabilities. But everything changed. On February 23, 2025, at the largest and most advanced facility for initiating thermonuclear reactions in California, at the so-called National Center for Plasma Ignition and Control, already the 7th attempt, a true miracle occurred. During a series of experiments, a significant increase in reaction efficiency was achieved. A powerful laser beam was directed at the target. Magnetic confinement is one of the main technologies used in the field of nuclear fusion. It employs strong electromagnetic fields to reliably and stably contain hot, superheated plasma, an ionized gas reaching extremely high temperatures, inside a specially designed container in the shape of a torus, which is familiar and recognizable to us. This plasma must remain within this closed space for an extended period, maintaining its properties and not escaping the magnetic field. This method allows for a stable plasma state over long durations, which is crucial for the development of practical next-generation thermal reactors. One of the most well-known and promising directions in this area is the project selected by the National Ignition Center, which favors inertial confinement of plasma. This approach uses a set of lasers, exactly 292 in total, each aimed simultaneously at a cylindrical capsule called PZU. Inside this capsule is a special fuel mixture composed of deuterium and tritium isotopes, two forms of hydrogen capable of reacting quickly and efficiently under certain conditions. The energy concentrated in the laser pulses compresses the capsule to such an extent that its density increases 50-fold compared to normal values. As a result of this compression, a fusion process, nuclear fusion, initiates, releasing a huge amount of energy. The main breakthrough is not only that the reaction was successfully initiated, this in itself is a significant achievement, but also that such reactions can now be reproduced repeatedly and stably, opening new horizons for practical and commercial applications. During the year 2024, some experimental setups already achieved an energy gain of up to 120%. That is, the energy output exceeded the energy input, and this trend only strengthened. Overall, the development trajectory of this field is upward, demonstrating steady progress and promising prospects for the future. Concurrently, other scientific groups and companies are working on advancing magnetic confinement. This technology is considered the most promising for large-scale energy installations. For example, in April 2025, TE Technologies announced the results of their experiment called NORM. During this research, the highest levels of plasma stability and resilience were achieved, using exclusively a neutral beam, without the complex quartz tube formation systems employed in previous developments, which complicated the design. This approach significantly simplified the device and, consequently, reduced its cost. Consider what this means. A simpler and less expensive technology makes it possible to scale up the installation, turning laboratory experiments into a commercial product. In turn, this opens the way for mass deployment and widespread use. Large investments from private capital enable continued progress. For example, Commonwealth Fusion Systems, which has raised over $2 billion from private sources, has successfully completed the assembly of magnetic confinement systems for its reactor designed to produce clean energy. This reactor, named Spark, is planned to be launched as early as the beginning of 2027. Such a significant influx of investment indicates market confidence in the prospects of nuclear fusion, since business does not invest in illusions or mirages but in the real future of energy. This moment marks a point of no return. We are moving from simple theoretical confirmations of the fundamental possibility of fusion to practical demonstrations of its commercial viability. We have entered an era when energy sources behave quite differently than before. Classical physics states that as complexity, costs, and environmental impacts increase, so does the energy density we can extract from traditional fossil fuels. Extracting oil, gas, or coal requires enormous efforts and involves complex processes. Just as nuclear fusion challenges our initial and perhaps most fundamental notions about energy generation, forcing us to reconsider the foundations of economics and physics, new discoveries related to celestial bodies profoundly and astonishingly influence our perspectives. The 3IATLAS small spacecraft currently in operation provoke deep reflections on the nature of small celestial bodies such as comets and asteroids. We believed we understood these objects well, knowing how ice and rock behave under pressure, radiation, and other cosmic factors. For decades, scientists have developed and refined theories and models to predict their behavior and characteristics. However, new data obtained from the 3IATLAS missions have demonstrated that these celestial bodies can be far more unusual and mysterious than all our previous notions suggested. The speeds, composition, emissions, and jets emanating from comets all suggest that either our models are incomplete and require refinement, or there is something unusual and as yet unaccounted for in the nature of these objects. All of this raises a troubling thought. Are we entering a new era in which anomalies, previously considered exceptions or rare phenomena, begin to serve as key signals? Perhaps we are only beginning to recognize and understand their significance. Let's consider the timeline of these events to grasp their importance and interconnections. In 2022, humanity achieved for the first time the ignition of nuclear fusion, a grand technological breakthrough promising a revolution in energy production. The following year, 2023, was marked by demonstrations of multi-node quantum teleportation networks, enabling information transfer at incredible speeds with virtually zero losses. In 2024, scientists successfully performed quantum teleportation over existing internet infrastructure, proving the possibility of scaling this technology beyond laboratory conditions and beginning its application in real-world systems. And in 2025, according to experts' forecasts, the reignition of nuclear fusion with advanced technologies will bring it closer to commercial implementation and widespread use. Simultaneously, in 2020, an experiment codenamed 3IATLAS was launched, which demonstrated behaviors of cosmic objects contradicting all existing models. Although these events are not causally linked, they are united by a common theme. They indicate that the universe operates with far greater flexibility and complexity than our current scientific theories suggest. Energy can now be released through nuclear fusion in ways previously deemed impossible to scale. Information can be transmitted via quantum channels alongside classical systems, opening new horizons in communications. Matter behaves as if it contains hidden layers of complexity or mechanisms of which we are only beginning to suspect. And all of this has occurred within just 1 year, evidence that these discoveries are interconnected and point to profound changes in our understanding of the laws of nature. These achievements and discoveries mean that in the foreseeable future, nuclear fusion will be able to provide us with clean, abundant, and virtually inexhaustible energy. Harnessing this energy, humanity will gain the ability to create large-scale quantum networks spanning the planet. Such networks could coordinate distributed measurements, computational processes, and control technologies that we cannot even imagine today. If objects similar to the 3IATLAS entities demonstrate that nature operates on hidden levels of complexity, then each new quantum network, each activated thermonuclear installation, and each deployed sensor complex could become tools for uncovering aspects of reality that we have overlooked or underestimated. In 2025, humanity faced phenomena that fundamentally alter our understanding of the cosmos and its laws. Among them, a particularly striking example is the mysterious object dubbed 3IATLAS. It arrived from interstellar space along a very unusual trajectory. This trajectory clearly obeys gravitational laws, yet it raises serious questions, as the supposed gravitational influence cannot be explained within existing theories. Disturbances in the gravitational field observed indicate the presence of forces acting on the object that should not be near its location. Thus, it appears that there are forces beyond the scope of conventional physical concepts at play along its path and around it. What is especially remarkable is that the flow of matter emanating from this object, its jet, remains continuous and coherent. There are no signs of chaos or randomness, which completely contradicts models applicable to comets and similar bodies. Typically, comets exhibit chaotic gas emissions caused by local and unpredictable surface heating, and their gas streams are quite heterogeneous in direction and intensity. However, in the case of 3IATLAS, we observe the formation of a complex, precise, and stable shape, as if created according to a clear design. The materials present in this object include substances that should not exist in standard comet formation scenarios. Substances incompatible under normal conditions and not found in objects formed in protoplanetary disks billions of years ago. The chemical composition of 3IATLAS, astonishingly, does not match what we expect to see in ancient cosmic bodies formed in the distant protoplanetary era. Its brightness, or more precisely, the intensity of its luminescence, fluctuates rhythmically in patterns that seem too regular and predictable to be random. These oscillations are not random bursts but manifestations of some internal order, which raises even more questions. Moreover, its trajectory has changed in ways that cannot be explained by known physical processes such as gas ejection or interactions with solar wind. The moments when the object alters its direction or accelerates appear to be caused by momentum transfer beyond what familiar physical laws permit. All of this is not merely observation. These are facts that categorically disprove long-standing models once considered reliable. These data are not measurement errors or inaccuracies. They are evidence that something fundamentally new and incomprehensible is happening. They do not require explanations as faulty observations. Instead, they should be perceived as signals indicating profound changes occurring in nature. These discoveries compel us to rethink our understanding of the universe, its structure, and its laws. In 2025, astronomers and physicists also made other significant breakthroughs that promise to propel science into a new phase. For example, the so-called dark stars, hypothetical objects surrounded by dark matter concentrated around primordial black holes, are truly exotic formations that completely alter our understanding of the diversity of stellar populations in the early universe. If such dark stars exist, then the cosmos contains entire populations of objects about which we have not even suspected, and their numbers could surpass those of ordinary stars by millions. Moreover, in 2025, a major technological breakthrough was finally achieved. Quantum teleportation transitioned from an experimental laboratory technology to a practical tool applicable over long distances, such as between megacities. Practical demonstrations show that transferring quantum states over distances of several tens or hundreds of kilometers is possible with high accuracy and stability. This proves that the laws of quantum mechanics are far more applicable to real-world use than previously assumed. This assumption proved to be so effective that it opened new horizons for our understanding of the world. Thanks to it, we have gained deeper insights into fundamental phenomena such as gravity, electromagnetism, quantum mechanics, and even the theory of relativity. These theoretical constructs, which sometimes seem complex and distant, have begun to be perceived, based on this assumption, as logical consequences of some of the most mysterious and fundamental laws of nature. However, a question arises. What if all this is nothing more than an illusion, and our assumptions and models built upon them are merely approximations that do not reflect the true nature of the universe? What if the anomalies we observe and try to explain with modern theories are not noise, random disturbances, or measurement errors, but signals pointing to some hidden reality? And what if our existing models, despite their internal consistency and verification, are essentially incomplete or even distorted, lacking crucial information about how our world is structured? Imagine that the universe turns out to be much stranger and more unusual than our familiar categories and concepts allow. Perhaps we are only beginning to realize the scale of this strangeness, and our usual picture of the world is just the tip of the iceberg. What if we consciously or subconsciously filter signals because we have been taught to perceive them as noise that prevents us from understanding the true nature of reality? Consider what we are accustomed to deeming natural. For example, a comet is undoubtedly a natural phenomenon. It is an icy and rocky body that, for unknown reasons, left its native star system and drifts through the endless cosmos between worlds. Or stellar mergers, these are also essentially natural processes. They feed the sun, produce new elements in the cores of stars, and create conditions for the birth of new planets. This process is one of the most fundamental and important in the entire universe, and its role is hard to overestimate. Quantum entanglement, seemingly, is an incredibly complex and mysterious phenomenon, but within quantum mechanics, it is considered quite natural. It is not a hypothesis but a verified and practically confirmed feature, proven countless times through experiments. But what if even such seemingly extraordinary phenomena as the three-IATLAS can be considered natural if we expand our understanding of that word? What if natural implies not only what fits into our current notions but also the very existence without human intervention? Then, such an atlas, appearing as if out of nowhere, is not an artificial object created by human hands but something that came to us from the depths of space. It is the result of a natural process that still remains a mystery to us. It came from the stars, and its existence defies our usual definition of artificial. However, its behavior contradicts everything we are used to believing about cosmic objects and raises questions about the nature of reality. This is where a deeper meaning lies. Are we mistaken in our assessments, and are we underestimating phenomena that do not fit into traditional classification frameworks? Astronomy, in essence, is a system of cataloging objects classified as stars, planets, asteroids, comets, black holes, neutron stars, brown dwarfs. Each of these objects is perceived as a separate category with specific properties and characteristic behaviors. Researchers group them accordingly, build models, and study patterns. But what if some objects fall into multiple categories or completely transcend their boundaries? And what if there are processes operating on scales about which we have not the slightest idea? Perhaps the 3IATLASes are just the first of a series of discoveries that do not fit into the existing scientific picture. Maybe the universe has long been showing us these unusual objects. Materials science, the study of the properties of substances and materials, is undergoing revolutionary transformations. New methods of creating and utilizing materials are opening unprecedented possibilities for humanity. The exploration of space is becoming not just a dream or fantasy, but a reality that is accessible and practically achievable. We are moving toward more extensive and deeper investigations of the universe, seeking answers to questions that have long intrigued humanity. If anomalies like the phenomenon known as 3IATLAS turn out not to be isolated exceptions but rather representatives of a much broader and more complex class of unexplained phenomena, then our existing models and theories, developed to understand the cosmos, cannot be considered complete or exhaustive. They lack entire categories of physics that could explain these unusual observations. We are not merely refining our knowledge, making it slightly more precise or expansive. We are beginning to realize that the universe holds dimensions and properties we previously could not even imagine. The discoveries we make sometimes seem incredible. What would its mass reveal if we tracked 3IATLAS? What new properties or laws will the Europa Clipper spacecraft uncover when it encounters this mysterious object? Or what will other similar bodies in the depths of our solar system reveal? These questions are not hypothetical or purely theoretical. They are important and demand answers. Their significance is hard to overestimate, as they concern the very essence of understanding what it means to be natural in a universe we are only just beginning to comprehend. The data collected in the coming weeks could radically alter our perceptions of comets, the movement of small bodies in space, and what these objects are truly capable of. Perhaps these observations will indicate that the 3IATLAS phenomenon is a harbinger of the discovery of a completely new type of cosmic objects, of which we had no prior suspicion. It is quite possible that anomalies are not mere exceptions but rather alarming signals that our current models of the universe and physical reality may be too incomplete, or even dangerously mistaken. The universe seems to be trying to tell us that our maps and knowledge lack entire continents, crucial for a full understanding of its structure. Our textbooks on physics, the theories and laws we trust, do not reflect the full complexity of processes. They are merely approximate models with significant limitations. Our categories and approaches are too narrow to encompass the full complexity and diversity of the cosmos. This is exactly how every great scientific discovery in human history begins, with an observation that does not fit into existing models. This deviation is perceived either as a random error or as a minor anomaly. Then scientists continue to observe, measure, and analyze, sometimes hoping to confirm a hypothesis, sometimes to understand the underlying cause of discrepancies. Ultimately, recognizing that their models and theories were insufficient or flawed, they take a step forward by developing new, more accurate, and comprehensive theories capable of explaining all observed phenomena. The stories of great discoveries are well known. Isaac Newton was slightly mistaken about the force of gravity, but only a little, and his theory laid the foundation for further research. Albert Einstein revolutionized the understanding of space and time, correcting and supplementing Newton's laws. Maxwell discovered electromagnetism, but quantum mechanics revealed that light and matter are far more entangled and complex than classical physics suggested. Each generation of scientists has faced the need to reevaluate their assumptions and expand the boundaries of knowledge. History shows that every major scientific achievement began with an observation that did not fit existing models and with the realization that,